Look at any deep field image from our most powerful telescopes. You see a tapestry woven with light, a cosmic jewel box overflowing with galaxies. They seem vibrant, clustered, almost close enough to touch neighbors in a grand cosmic city. But this is a grand illusion. It's a trick of perspective, a beautiful lie that hides an emptiness so vast it challenges our very understanding of reality. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. What if I told you that the silent, dark space between the galaxies is far more important and holds a much deeper secret than the galaxies themselves? We celebrate these islands of light, but we ignore the ocean of darkness they float in. So, how empty is that ocean? What would it be like to travel through it? And what does this immense nothingness tell us about the ultimate fate of everything? The answers will not just change how you see the night sky. They'll change how you see existence itself. The grand illusion of proximity. To start this journey, we have to break the illusion. We have to recalibrate our minds to a scale that feels alien, a scale our brains weren't built for. Let's begin with our closest large neighbor. Not a star, but our sister galaxy, Andromeda. In photos, it's a majestic spiral that seems to fill the frame. It looks close. But close, in cosmic terms, is a deeply misleading word. The Andromeda Galaxy is about 2.5 million light-years away. Let's explain that slowly. A single light-year is the distance light travels in 1 year. Light is the fastest thing in the universe, moving at an almost instant 300,000 kilometers, or 186,000 miles, every single second. In 1 year, a photon of light travels nearly 9.5 trillion kilometers, or about 6 trillion miles. That's 1 light year. Now, multiply that by 2.5 million. The number is so big it becomes meaningless. So, let's try an analogy. Imagine our own galaxy. The Milky Way is the size of a large dinner plate, about 12 inches, or 30 centimeters, across. On this scale, where our entire solar system is smaller than a grain of salt, where would the Andromeda Galaxy be? Another plate on the same table? In the same room? No. On this scale, the Andromeda dinner plate would be over 25 feet, or about 6 meters, away. Imagine 2 dinner plates separated by the length of a large truck, and in the space between them, almost nothing. Just a few tiny, grain of sand-sized dwarf galaxies. Andromeda is our nearest major galactic companion. It's part of what we call the local group, a small collection of about 80 galaxies bound by gravity. But most galaxies aren't our neighbors. They're strangers, separated by distances that make the gap to Andromeda look like a stone's throw. When the Hubble or James Webb Space Telescope takes a deep field image, it stares at a tiny, seemingly empty patch of sky for hundreds of hours. That patch is like looking at a grain of sand held at arm's length. And in that minuscule window, thousands of galaxies appear. This is what creates the illusion. The telescope is looking through an immense cone of space, billions of light-years deep. Some galaxies in the image are closer, while others are incredibly far, their light having traveled for over 13 billion years to reach us. The photograph flattens this unfathomable depth onto a single, two-dimensional plane. It's like taking a picture of a long, straight road from the front. All the cars seem bunched together, but in reality, they're separated by miles of empty asphalt. The average distance between major galaxies is tricky to pin down, as it depends on whether they are in a dense cluster or out on their own. Within clusters, it can be a few 100,000 to a few million light years. But the cosmos isn't uniform. It has a structure. And understanding that structure is the key to understanding its emptiness. The cosmic web, the architecture of emptiness. For a long time, astronomers figured galaxies were scattered more or less randomly, like marbles tossed on the floor. But as we got better at mapping the universe in 3 dimensions, a stunning structure began to emerge. We call it the cosmic web. Imagine a sponge. It's not a solid block. It's made of dense filaments that connect and twist into a complex, web-like structure. But most of the sponge's volume isn't the sponge itself, it's the empty holes in between. The universe, on its largest scales, is exactly like this. The stuff of the sponge is made of galactic superclusters, gargantuan collections of thousands of galaxies, all bound together by gravity. These superclusters aren't isolated, they're linked by immense, river-like structures known as galaxy filaments. These filaments are the largest known structures in the universe, stretching for hundreds of millions of light years. They are the highways of the cosmos, channels along which galaxies and dark matter flow. Our own Milky Way is inside a supercluster called Laniakea, a name that means immeasurable heaven in Hawaiian. It contains over 100,000 galaxies and stretches for more than 500 million light years. We are a single speck in this heavenly structure. But the most profound part of the cosmic web is not the filaments or the clusters. It's the empty space between them. These are the cosmic voids. If the filaments and clusters are the sponge, the voids are the holes. And these holes are mind-crushingly enormous. A typical void can be hundreds of millions of light years across. To go back to our dinner plate analogy, if the Milky Way is a plate, a cosmic void would be a vast, empty sphere hundreds of miles wide. Inside it, there would be almost nothing. No other dinner plates. No major galaxies at all. This isn't an exaggeration. Voids are the largest scale structures in the universe, defined by their profound emptiness. The grand cosmic web, this beautiful tapestry of light, is mostly nothing. The brilliant filaments of galaxies are just delicate threads outlining the colossal, dark chasms that dominate the universe. So, when we ask, how big is the space between galaxies? The answer gets complicated. Within a cluster or filament, they can be relatively close. But the space between the filaments, which makes up most of the universe's volume, is a completely different kind of empty. A journey into the void. Let's take a journey. Imagine a starship that can travel faster than light. We'll start in our cosmic neighborhood, the Milky Way, and head out into the great intergalactic ocean. As we leave our galaxy, the view is spectacular. Behind us, the glowing spiral of the Milky Way, with its hundreds of billions of stars, fills our viewport. In front, the blackness is punctuated by the faint smudges of other nearby galaxies in our local group. We set our course for the edge of our Laniakea supercluster. For a time, the journey isn't crowded, but we're never truly alone. We pass galaxies of all shapes and sizes. Then, we reach the edge. The river of galaxies thins out. The smudges of light become fewer and farther between. And then, we cross the threshold. We have entered a cosmic void. The change is absolute. Behind us, the Laniakea supercluster shrinks until it's just another faint, shimmering thread in the distance. In front of us, and to every side, there is nothing. Not just the mostly empty space between stars in a galaxy. This is a different order of emptiness. The blackness is deeper, more complete than anything you've ever known. No nearby stars, no nebulae, no galaxies. You could travel for 1 million light years and see nothing. 10 million light years. Nothing. 50 million light years. Still nothing. The silence and darkness are absolute. The numbers here are staggering. If you took all the matter in the entire observable universe, every star, planet, black hole, and all the dark matter, and spread it out evenly, the average density would be about 1 hydrogen atom per cubic meter. A cubic meter is about the size of a closet. Imagine a closet with just 1 atom in it. That's the asterisk average density. But a cosmic void is far, far emptier than that. In the deepest parts of a void, the density can be 10, or even 100 times, less than the cosmic average. You could fly for millions of years at the speed of light through a volume of space the size of a planet and not hit a single atom. It's the most perfect vacuum in nature. An emptiness so profound it's hard to even call it space. It's the absence of things. For millions of years, our starship would drift through this unending night, with the only light coming from the impossibly faint glow of the cosmic web we left behind and the one we are heading towards. This journey across a typical void, say 300 million light-years wide, would be a journey through the heart of cosmic loneliness. It would show you the fundamental truth of our universe. Galaxies are the exceptions. The rule is the void. The universe isn't a collection of galaxies, it's a collection of voids, merely outlined by galaxies. But here, in the heart of this perfect, absolute nothingness, is where our story takes its most dramatic turn. Because this emptiness isn't empty at all. The paradox of nothing, a revelation of energy. For centuries, we thought a vacuum was just the absence of matter. Empty space was just empty. But 20th century physics turned that idea on its head. Quantum mechanics revealed that on the smallest scales, empty space is a bubbling, frothing sea of energy. Even in a perfect vacuum, virtual particles constantly pop into and out of existence, borrowing energy from spacetime itself. The vacuum, it turns out, has energy. It's alive with quantum fields. You can remove all matter and radiation, but you can never remove the fields themselves. They're woven into the very definition of space. So even in the heart of a cosmic void, you are swimming in an ocean of pure potential. But this subtle energy isn't the biggest secret the void is hiding. There's something else here. Something far more powerful and mysterious, that dominates the entire universe. We call it dark energy. In the late 1990s, astronomers were trying to measure how quickly the universe's expansion was slowing down. Everyone assumed it was slowing. Gravity, after all, should be acting like a brake. Two separate teams set out to measure this deceleration. But they found something that broke cosmology. The expansion wasn't slowing down. It was speeding up. This discovery was so profound it won the Nobel Prize. It meant there had to be some unknown energy, some repulsive force built into space itself, pushing the universe apart. It acts like anti-gravity. This mysterious force was named dark energy. Through various measurements, we've figured out how much of this stuff there is. The results are shocking. All the matter we can see, stars, galaxies, you and me, makes up less than 5% of the universe. About 27% is dark matter. The rest of it, a staggering 68%, is dark energy. Our universe is overwhelmingly dominated by this invisible, repulsive energy. And now we come back to the voids. Where does dark energy have the biggest effect? In dense superclusters, gravity is king, easily overpowering dark energy's subtle push. That's why the Milky Way and Andromeda are on a collision course, not expanding away from each other. But out in the great cosmic voids, it's a different story. There's almost no matter and no gravity to fight back. In the absence of gravity's restraining hand, dark energy is free to do its work. This is the great paradox. The emptiest places in the universe are actually where the cosmos's dominant energy is most powerful. They aren't empty at all. They are full of the invisible, accelerating force that is shaping the destiny of our entire universe. The nothing is, in a very real sense, the most important something there is. This has also led to a potential explanation for a big crisis in cosmology, the Hubble tension. Measurements of the early universe suggest one expansion speed, but measurements of the modern universe show it's expanding about 8 to 10% faster. Some new research suggests that if our own Milky Way is in a large, underdense region sometimes called the KBC void, this could explain the difference. The lower density would mean less local gravity to resist dark energy's push, making our patch of the universe expand faster than the average. While this idea is still being debated, it shows how the great emptiness might be shaping our very perception of reality. The architect of our fate. This revelation that voids are full of an accelerating energy has profound consequences for the future. The dominance of dark energy means the voids are growing. They are actively pushing against the cosmic web, stretching the space between superclusters. Slowly but surely, dark energy is winning the cosmic tug-of-war against gravity. Over billions of years, this will dramatically change the universe. The great filaments of the cosmic web will be stretched and thinned until they snap. The superclusters, once connected, will become isolated islands in an ever-expanding ocean of darkness. What does this mean for us? For a few billion years, not much will change. The galaxies in our local group will continue to merge, with the Milky Way and Andromeda set to collide in about 4-5 billion years to form a new, giant galaxy nicknamed Milkomeda. But on the grandest scale, the universe will become an increasingly lonely place. As the voids expand, they will push other galaxy clusters away from us faster and faster. Eventually, the most distant clusters will recede so quickly their light can no longer reach us. One by one, they will vanish from our sky. Their light will be stretched beyond our ability to see it, redshifted out of existence over the cosmic horizon. The sky, now filled with the light of billions of galaxies, will begin to grow dark. Over tens, then hundreds of billions of years, this will continue. Cluster after cluster will disappear. Eventually, every single galaxy outside our own gravitationally bound local group will be gone. Our distant descendants, living in the great Milkomeda galaxy, will look out into the night sky and see nothing. Just the stars of their own galaxy, and an endless, terrifying blackness beyond. They would have no way of knowing other galaxies ever existed. All of cosmic history, all evidence of the Big Bang and the cosmic web, will have been erased by the relentless expansion of the void. The universe will return to a state of profound emptiness, not because it's empty, but because the energy in the emptiness has pushed everything apart. The ultimate fate of the cosmos is not fire, but ice. A cold, dark, and lonely existence, driven by the power hidden in the space between the galaxies. The universe is a place of incredible paradoxes. The brightest lights are born from dark clouds, and the emptiest spaces hold the power that will decide our ultimate fate. Exploring these ideas changes our place in the cosmos. If this journey through the void has expanded your perspective, I hope you'll join us for more explorations into the universe's deepest secrets. We started with a simple question: how big is the space between galaxies? We began with the illusion of galaxies clustered in a photograph. We journeyed across incomprehensible scales and through a cosmic web woven from threads of light. We plunged into the heart of a cosmic void, an emptiness bordering on absolute. And there, in that perfect nothingness, we found the key to everything. The space between galaxies isn't an absence.
It's a presence. It's the arena where the fundamental battle between gravity and dark energy is being waged. And it's the place where dark energy is winning. The beautiful structures we see today, the clusters and filaments, are temporary. They are fleeting patterns destined to be dissolved by the voids they outline. The grand illusion of proximity in our telescopes will be replaced by the reality of total, unending isolation. But there is a strange beauty in this. It tells us that we live in a special time, a privileged era in the universe's long history, where we can still see the grand tapestry in all its glory. We are, for now, not alone. We can look out and see the light from billions of other islands in the great cosmic ocean. The space between them is vast, dark, and powerful. But for now, the light can still cross it. And in that light, we can read the history of our universe and glimpse its ultimate destiny, all written in the beautiful, terrible, magnificent space between the galaxies. Part 2. How far away are the nearest galaxies? The strangest thing about the universe is not that it contains so much light. It is that the light is spread so thin. When we first begin looking at astronomy, galaxies can seem almost familiar. We see photographs of Andromeda as a graceful spiral, suspended in blackness, and something in the mind quietly assumes it is far away in the same way a mountain is far away. Distant, yes, but still part of the same visible landscape, still somehow nearby. And that instinct is completely understandable. Our brains were built for forests, shorelines, weather, footsteps, and horizons. They were not built for millions of light years. They were not built for objects so distant that the light arriving here tonight left long before human civilization existed in anything like its present form. They were not built for the idea that the nearest major galaxy is not simply far, but so far that the word far begins to lose all of its meaning. And so, in this quieter stretch of our journey, we are going to slow down and do something simple. We are going to take the idea of a neighboring galaxy and gently unfold what that really means. We will begin close to home, with distances our minds can almost hold, and then step outward, farther and farther, until even our nearest galactic neighbors begin to feel like islands separated by an ocean too large to cross with ordinary thought. If these slow explorations help ease you into sleep, you are always welcome to like the video, subscribe, or leave a comment about where in the world you are listening from tonight. There is something quietly comforting about imagining these thoughts drifting out into bedrooms, cities, coastlines, and quiet corners all over Earth. So let us begin where scale still feels human. The Moon, our nearest celestial companion, is about 384,400 kilometers away. That already sounds large, and in ordinary life it is. If you were to drive to the Moon, without oceans or gravity or the impossible mechanics of such a journey getting in the way, and if you could somehow keep driving at highway speed without stopping, the trip would take many months. Light, by contrast, reaches the Moon in a little over 1 second. Already, there is a difference between human scale and cosmic scale. Now move outward to the Sun. The Sun is about 150 million kilometers away from Earth. Light from the Sun takes about 8 minutes and 20 seconds to arrive here. The warmth on your skin on a bright afternoon began as energy released inside the Sun more than 8 minutes earlier. So even sunlight, which feels immediate, is already a message from the recent past. Beyond the Sun are the outer planets. Neptune, depending on where it is in its orbit, is so far away that sunlight can take more than 4 hours to reach it. And yet even Neptune is still well inside our own small cosmic neighborhood. Even Neptune is still inside the thin shell of our own solar system. Then we step beyond the solar system, and scale changes again. The nearest star system to us, Alpha Centauri, is about 4.37 light-years away. A light-year is not a measure of time. It is a measure of distance. It is the distance light travels in 1 year, moving through the vacuum of space at about 300,000 kilometers per second. In 1 second, light could circle Earth more than 7 times. In 1 minute, it could travel to the Moon and back several times. In 1 year, it covers nearly 9.46 trillion kilometers. That is 1 light year. And Alpha Centauri is more than 4 of those away. Inside a galaxy, this is normal. Stars are not packed tightly together like street lamps in a city. They are spread across extraordinary emptiness. Even within the Milky Way, The typical distance between stars in our region is measured in light years. Our own galaxy, the Milky Way, is roughly 100,000 light years across. That means even our home galaxy is already so immense that if a beam of light began traveling from one side to the other, it would take about 100,000 years to complete the crossing. Try to rest with that for a moment. Light, the fastest thing we know, crossing our galaxy for 100,000 years. And yet, astonishingly, when we speak of other galaxies, we are no longer speaking in tens of thousands of light years. We are speaking in millions. The nearest large galaxy to the Milky Way is Andromeda, also known as Messier 31. It is about 2.5 million light years away. This means the light entering your eyes from Andromeda tonight began its journey roughly 2.5 million years ago. At that time, early human ancestors were walking the Earth. Entire branches of human history had not yet unfolded. No cities, no writing, no music carried through walls, no telescopes, no satellites, no whispered bedtime questions about the universe. And still that light kept traveling. Year after year, age after age, crossing the dark, until finally, on one quiet night, it arrives here. This is one of the reasons astronomy feels so dreamlike. When you look out into space, you are not only looking far away, you are looking back in time. Distance and history become the same thing. The farther away an object is, the older the story it is telling. Andromeda is our sister galaxy in a broad gravitational family we call the Local Group. It is the nearest major spiral galaxy to our own, and it contains perhaps 1 trillion stars, though estimates vary. In images, it can appear delicate, even compact, because the sky compresses distance. But Andromeda itself is enormous, spanning roughly 220,000 light years from one side to the other. In some ways it may even be larger than the Milky Way. So here is the quietly astonishing image: one giant galaxy containing hundreds of billions, perhaps 1 trillion stars, floating 2.5 million light years away from another giant galaxy that contains hundreds of billions of stars of its own. 2 star cities, 2 continents of light, separated by a darkness so vast that ordinary language starts to fail. There are, of course, galaxies even closer than Andromeda if we count smaller companions. The Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, is about 160,000 light years away. The Small Magellanic Cloud is around 200,000 light years away. These are not major galaxies like the Milky Way or Andromeda, but they are true galaxies nonetheless, smaller islands of stars traveling in our wider neighborhood. Even those smaller companions are astonishingly distant. 160,000 light years sounds, at first, much more manageable than 2.5 million. But that is only because the mind has not yet attached any real feeling to either number. In lived human terms, both are effectively beyond reach. Both are so remote that our best daily intuitions collapse almost immediately. This is why analogies matter. Imagine shrinking the Milky Way down to the size of a large dinner plate. Not a star. Not our solar system. The whole galaxy. One plate. On that same scale, Andromeda would be another dinner plate several meters away. Not beside it. Not almost touching. Not even in the same cluster on a shelf. It would be across the room. And in the dark space between those 2 plates, there would be almost nothing at all. That image matters because it corrects one of the most persistent illusions in astronomy. We think galaxies are packed into space because photographs flatten them into a single visual field. But flattening is deceptive. A deep image of the sky can contain galaxies that seem close together in the picture while being separated by unimaginable depth. It is like looking down a long road at night and seeing many distant lights from different towns appear almost side by side, when in reality they are scattered over enormous distances. Perspective creates the illusion of closeness. Distance restores the truth. Andromeda is not alone in our local group. There is also the Triangulum Galaxy, or Messier 33, another spiral galaxy located about 2.7 to 3 million light-years away, depending on the measurement used. It is smaller than both the Milky Way and Andromeda, but still immense on a human scale, containing tens of billions of stars. Around these larger galaxies are dozens of dwarf galaxies, faint companions gathered into the same broad gravitational community. The local group itself stretches across roughly 10 million light-years. That phrase is easy to say, 10 million light-years, but it helps to slow it down. Our own solar system, even if we include its distant outer reaches, is tiny on this scale. Our galaxy is large, but still only one member of this wider family. The local group is the first reminder that even a galaxy is not the final unit of structure. Galaxies gather, groups gather, clusters gather, and beyond them, much larger patterns begin to appear. But for now, let us stay with the nearest neighbors, because they are already enough to humble the mind. Suppose you wanted to travel to Andromeda. At the speed of a passenger jet, the trip would take far longer than human civilization has existed. At the speed of the Voyager 1 spacecraft, one of the fastest human-made objects ever launched, the journey would still take tens of billions of years, much longer than the current age of the universe. Even at the speed of light, the absolute cosmic speed limit as far as we know, you would need 2.5 million years. So when people speak casually of neighboring galaxies, the word neighboring belongs entirely to gravity and cosmology. It does not belong to human travel. It does not belong to any practical sense of nearness we experience in ordinary life. These are neighbors only in the way that two remote islands in a vast ocean might be called neighbors because there is nothing else around for an even greater distance. And yet even in this emptiness, there is motion. The Milky Way and Andromeda are not fixed forever in stillness. They are moving toward one another at about 110 kilometers per second. Over unimaginable spans of time, gravity is slowly drawing them together. In about 4 to 5 billion years, the two galaxies are expected to begin a long interaction that will eventually reshape them into a single larger galaxy. This can sound dramatic, almost violent, but even a galactic collision is mostly a dance through emptiness. Galaxies are made of so much open space that stars within them usually do not crash directly into one another. Instead, their mutual gravity distorts their shapes, draws out long tidal streams of stars, and gradually rearranges the whole structure. Even collisions between galaxies are governed by emptiness. That is worth lingering on. The universe is so spacious that even when galaxies meet, most of what they bring to the encounter is not solidity, but distance. The same is true when we speak of the gap between the Milky Way and Andromeda. We are not imagining a clean, hard boundary at the edge of each galaxy and then a perfect void between them. Galaxies are surrounded by vast halos of dark matter, thin regions of gas, scattered stars, globular clusters, and invisible gravitational influence extending far beyond the bright spiral structures we usually picture. So the boundary between one galaxy and true intergalactic space is not like walking out of a building. It is more like leaving a city and slowly entering countryside, then deep wilderness, then open ocean. The lighted center fades first. Then the outskirts thin out. Then there is mostly dark. And then the long crossing begins. This is part of why the nearest galaxies matter so much to the imagination. They are close enough to name, to map, to place in our cosmic family tree. But they are still so far away that they reveal the real architecture of the universe. The universe is not a crowded chamber full of glowing objects pressed together in blackness. It is a place where immense structures drift in a sea of distance. The light is rare. The dark is common. And galaxies, for all their grandeur, are more like exceptions than the rule. Perhaps one of the calmest ways to feel this is to think about the night sky itself. Most of the stars you see with your own eyes belong to our own Milky Way. They feel numerous, but they are local in cosmic terms. Other galaxies are usually too faint to notice without dark skies or optical aid, and that faintness can trick us into assuming they are small or unimportant. But faint does not mean small. It often means remote. Andromeda, for example, is one of the few galaxies visible to the unaided eye under dark conditions. When you glimpse it, you are not seeing a tiny object. You are seeing a vast spiral system containing hundreds of billions of stars, so distant that its enormous scale has been reduced to a soft smudge. You are seeing immensity hidden by distance. That may be one of the deepest lessons in astronomy. Distance makes giants look small, and so much of understanding the cosmos is simply learning not to trust first impressions. A galaxy that looks like a faint blur may be larger than anything the human mind naturally knows how to imagine. A darkness that looks empty may span millions of light years. A nearby neighbor may in fact be unreachable by any journey we know how to make. Once that truth settles in, the phrase space between galaxies begins to change its meaning. It stops sounding like a decorative bit of emptiness, some minor gap between more important things. It begins to sound like the main event, the dominant feature, the real architecture. Not a crack between stones, but the desert between cities. Not a pause between words, but the silence in which the words are briefly spoken. And that is where our path leads next. Because once we understand how far away even the nearest galaxies really are, an even quieter question rises into view. What is actually out there in the dark between them? Is it truly nothing? Or is the void itself more subtle than it first appears? That is where we go next. Part 3. What exists between galaxies? Once you begin to understand how far away the nearest galaxies really are, a quieter question naturally follows. What is actually out there in the distance between them? When most of us imagine the space between galaxies, we picture a kind of perfect nothing, a black, silent emptiness, a vast stretch of absolute absence, with no substance at all, just darkness laid across unimaginable distance. And from a human point of view, that is a very reasonable image. Compared to Earth, compared even to the air in an empty room, the space between galaxies is so astonishingly empty that calling it nothing feels almost fair. If you could drift into that darkness, you would not find clouds to walk through, winds to feel, or landscapes to cross. You would not see a glowing mist spread evenly from one galaxy to the next. You would not find a cosmic ocean in the ordinary sense, with visible waves or flowing currents or anything dense enough to remind you of sea or sky. You would mostly find darkness. And yet, as so often happens in astronomy, the first impression is only half the truth. Because the space between galaxies is not truly empty. Not in the strictest sense. Not in the way we imagine a blank page or an abandoned room. It contains matter. It contains energy. It contains radiation, magnetic fields, drifting particles, invisible structure, and the faint remains of processes so ancient and so large that they can be difficult to hold in the mind all at once. So the real answer is gentler and stranger than simple emptiness. The void between galaxies is not nothing. It is almost nothing. And that difference matters. If these slow journeys into the universe help you relax, settle down, or drift into sleep a little more easily, you can always leave a like, subscribe, or mention in the comments where you are listening from tonight. There is something quietly beautiful about imagining these thoughts moving through apartments, quiet houses, late-night offices, hotel rooms, rainy cities, and distant coastlines all at once. Now let us move gently into the dark and ask what is truly there. The first thing to understand is that space between galaxies is not the same as the space inside a galaxy. Even within the Milky Way, the distance between stars is immense, but the galaxy is still filled with more than stars alone. There are gas clouds, dust lanes, magnetic fields, cosmic rays, planets, comets, black holes, and all the scattered debris of billions of years of stellar life. A galaxy is not crowded by human standards, but compared to the deep intergalactic dark, it is almost busy. The space between galaxies is thinner, quieter, and far more diffuse. Astronomers often call this realm the intergalactic medium. That phrase sounds technical at first, but its meaning is simple. It is the material that exists in the vast spaces between galaxies. Not much material, but some. A faint, extremely thin presence spread across distances so large that even a very small amount of matter, when stretched across the cosmos, becomes part of a meaningful structure. And what is that material mostly made of? Mostly hydrogen. This is fitting, in a way. Hydrogen is the simplest and most abundant element in the universe. One proton, one electron. The most modest beginning. Most of the ordinary matter in the universe started, in one form or another, with hydrogen. Stars are born from it. Galaxies are shaped by it. And even in the deep spaces between galaxies, hydrogen remains, sparse and lonely, still carrying the memory of the early universe. But intergalactic hydrogen is not usually drifting around as comfortable, neutral atoms the way we might casually imagine. Much of it exists as plasma, a state in which electrons have been stripped away from atoms. This means intergalactic space is not filled with tiny, peaceful marbles of matter, but with charged particles moving through a nearly perfect vacuum. The universe, in this sense, is less like a static painting and more like a quiet electrical environment, subtle and almost impossible to notice directly, but never entirely still. That may be one of the most important themes in understanding cosmic emptiness. The void is quiet, but it is not dead. There are particles moving through it. There is energy passing through it. There are processes unfolding across millions and billions of years with such patience that they can seem motionless from the small, hurried perspective of human life. Imagine leaving the Milky Way and drifting outward, farther and farther beyond its luminous disk. At first the galaxy would still feel present behind you, a broad architecture of stars fading slowly into distance. You might pass through the outer halo, through regions where stars are scarce and matter grows thinner. And then, gradually, the familiar structure would loosen its hold. The galaxy would no longer feel like a place around you. It would become an object behind you. Ahead, there would be darkness. But not a perfect black. Not entirely. Because space itself is crossed by light, even when there are no nearby stars. Some of that light is ancient. Some of it is the accumulated glow of distant galaxies, too faint and too far to stand out individually. Some of it is radiation left over from the early universe itself, the cosmic microwave background, a faint afterglow from a time long before galaxies fully formed. This ancient light fills all of space. It is everywhere, even in the darkest void. It is weak, cold, and invisible to human eyes, but it is there. A soft relic from the young universe, still passing through every region of the cosmos. So even in the emptiness between galaxies, the universe is not silent in every sense. It is bathed in a whisper of old light. And there is more. There are cosmic rays, fast-moving particles launched by violent events like supernova explosions, active galaxies, and other energetic processes. These particles can travel extraordinary distances through space. Most of the intergalactic void is not buzzing in any dramatic or visible way, but from time to time, particles born in violence can cross the deep quiet, carrying the energy of ancient explosions through darkness that seems otherwise undisturbed. There are also magnetic fields, faint and difficult to map, but real. Space is not simply a blank stage on which matter performs. It has texture, structure, tension, and field. Even where matter is almost absent, invisible influences can remain. And then there is dark matter. This is where the story becomes even stranger, because much of what shapes the large-scale structure of the universe is not ordinary matter at all. Galaxies do not merely float through empty space according to the gravity of the stars and gas we can see. They are embedded in much larger halos of dark matter, invisible to telescopes but detectable through their gravitational influence. Dark matter helps organize the cosmic web. It helps guide where galaxies form, how they cluster, and how matter gathers across immense scales. So when we talk about the space between galaxies, we are not speaking about a region completely untouched by structure. Much of that space is threaded through by the unseen architecture of dark matter. It does not glow. It does not scatter light in any familiar way. But it seems to be there, shaping the universe from behind the curtain. This gives the emptiness a different character. The darkness is not random. It is organized. It has a hidden skeleton. In a calm and almost philosophical sense, this is one of the universe's recurring lessons. What looks empty from a distance often turns out to be subtly occupied. What looks silent often turns out to be full of faint and patient activity. The cosmos is not eager to reveal itself at first glance. It rewards slow attention. And that is especially true here, in the dark between galaxies. Another quiet truth is that galaxies do not keep all their material neatly to themselves. Over billions of years, galaxies interact. Gravity pulls on them. Stars explode. Black holes feed and release energy. Gas gets heated, stirred, and sometimes thrown far beyond the bright visible boundaries of the galaxy itself. So the space between galaxies can contain matter that was once more firmly held inside galaxies. In galaxy clusters, this becomes especially important. A galaxy cluster is not simply a collection of galaxies floating together in emptiness. It is also filled with tremendously hot gas spread throughout the cluster. This gas can reach temperatures of millions of degrees, so hot that it emits X-rays. In fact, in some galaxy clusters, there is more mass in this hot intracluster gas than in all the stars of the galaxies combined. This means that some of the matter associated with galaxies is not inside galaxies at all, but in the vast spaces between them. This is a remarkable idea. If you looked at a galaxy cluster with ordinary eyes, you might think the galaxies are the whole story. Bright islands in blackness. But much of the ordinary matter may be floating invisibly around and between them, heated to extraordinary temperatures, too thin to see directly with human vision, but still very real. So the darkness between galaxies can contain not only isolated particles, but whole diffuse atmospheres stretched across the scale of clusters. There is a calm irony in that. The emptiest looking places can hold enormous amounts of matter, provided that matter is spread thinly enough. And thinness is the key. Everything about the space between galaxies comes back to scale. On Earth, we are used to matter being concentrated. Air fills rooms. Water fills glasses. Stone fills walls. Even a cloud in the sky, light as it seems, is dense by cosmic standards. But in intergalactic space, matter is diluted across distances so immense that it becomes almost ghost-like. It is present, but barely. A trace. A suggestion. This is why the word vacuum can be misleading if we do not use it carefully. We sometimes say that outer space is a vacuum, and in a practical sense that is true. But the vacuum between galaxies is far better than any vacuum we can create on Earth. In laboratories, even the most advanced vacuum chambers still contain vastly more particles than the emptiest natural regions of space. Earthly emptiness is still crowded by comparison. The best vacuum we build is, from the point of view of a cosmic void, still thick with matter. That can be hard to picture because our daily sense of empty is so limited. An empty room is full of air. An empty bottle still contains gas. A seemingly empty sky still holds moisture, dust, and molecules. The space between galaxies, by contrast, is emptiness refined to an almost unimaginable degree. And yet it is still not perfect absence. Now and then, objects move through this darkness in lonely isolation. There can be rogue stars, stars that have been thrown from galaxies by gravitational encounters. There may be wandering black holes, carried out from past galactic mergers or violent interactions. There can be dwarf galaxies so faint and sparse that they barely stand out against the dark. Even planets, in theory, could be cast adrift, no longer bound to a star, moving through the cold night between systems and perhaps, over even longer timescales, between galaxies. This does not mean intergalactic space is populated in any rich or frequent way. Far from it. The point is almost the opposite. The very fact that such objects feel surprising tells us how rare they are out there. To encounter a lone star in the dark between galaxies would not make the void feel full. It would only make the emptiness around that star feel even deeper. A single candle in a desert of night does not erase the desert. It reveals it. And perhaps that is the emotional force of this whole topic. The space between galaxies asks us to accept a scale on which even presence can feel like absence. A few particles per cubic meter, a faint radiation field, a distant stray star, a hidden web of dark matter, some hot gas in a cluster, a passing cosmic ray. These are real things. But against the immensity of the dark, they still leave the overwhelming impression of nearly perfect emptiness. That impression is not wrong. It is just incomplete. There is also a deeper historical story written into this thin material. The intergalactic medium is not merely leftover clutter. It is part of cosmic history. In the early universe, before galaxies fully assembled, matter was spread much more smoothly. Over time, gravity gathered that matter into denser regions, forming stars, galaxies, and clusters, while other regions were left emptier. So the material between galaxies is not separate from the story of galaxies. It is part of the same long process. Some matter fell inward into luminous structures. Some remained stretched out. Some was heated, expelled, or redistributed by the life cycles of galaxies themselves. In that sense, the dark between galaxies is not just space between destinations. It is a record of how the destinations came to be. Even the chemical story of the universe touches this emptiness. The earliest universe made mostly hydrogen and helium, heavier elements, the carbon in life, the oxygen in air, the iron in blood, had to be forged later inside stars. Over time, supernova explosions and galactic outflows pushed some of these heavier elements outward. That means the intergalactic medium, faint as it is, can contain traces of star-forged material. The products of ancient stellar lives can drift through the dark between galaxies, spread so thinly that they are almost impossible to imagine, but still present. So when you ask what exists between galaxies, the answer becomes something like this. There is hydrogen, often ionized into plasma. There is helium. There are sparse traces of heavier elements. There is diffuse gas, sometimes heated to enormous temperatures in clusters. There is radiation from distant sources and from the early universe itself. There are magnetic fields. There are high-energy particles. There is the invisible scaffolding of dark matter. And perhaps, here and there, lonely wandering objects moving through the dark. It is not much. But it is not nothing. And maybe that distinction matters beyond astronomy. Because human intuition often divides reality too sharply. Full or empty. Something or nothing. Presence or absence. The universe seems less interested in those clean boundaries. Again and again, it gives us gradients, thresholds, and almosts. The intergalactic void is not a packed realm of substance, but neither is it a blank. It is a quiet middle state, nearly empty, deeply dark, yet still carrying matter, light, energy, and history. That is what makes it beautiful. A perfect void would be easier to understand, but perhaps less interesting. This nearly empty universe, by contrast, feels more alive. It is subtle enough to be humbling, sparse enough to be haunting, and real enough to remind us that darkness is not the same thing as nothingness. As we drift deeper into this question, another one begins to rise. If there is matter between galaxies, just how much is there? How thin is thin, really? How empty is almost empty? Because saying that intergalactic space contains gas and particles is one thing, feeling the true scale of that emptiness is something else entirely. And to feel it, we have to go beyond naming what exists and begin asking about density. Not just what is there, but how unbelievably little of it there is. That is where we go next. Part 4. How empty is the space between galaxies, really? There is a strange moment that happens in astronomy when a fact sounds clear, but still does not feel real. You hear that space between galaxies is thin. You hear that matter out there is incredibly sparse. You hear that the void is almost completely empty. And intellectually, you understand the sentence. The words make sense. But something deeper in the mind remains untouched. It nods politely and moves on, because it still has not actually felt the scale of what is being described. And that is where we are now. We know that the space between galaxies is not truly nothing. It contains a faint intergalactic medium, a whisper of gas, a scattering of particles, old radiation, invisible structure, and the lingering memory of cosmic history. But saying that something exists there can accidentally make it sound fuller than it really is. It can create the impression of a very thin mist, perhaps, or a wide but gentle fog stretched across the dark. The truth is much more severe than that. The space between galaxies is so empty that even calling it a vacuum barely captures the depth of its emptiness. So in this part of the journey, we are going to slow down and ask a more precise question. Not simply what is there, but how much is there? How thin is the thinness? How empty is the emptiness? And why the numbers involved are so far beyond everyday experience that the only way to approach them is through comparison, patience, and a willingness to let the mind stretch a little farther than it is used to going. If these quiet cosmic explorations help you settle into sleep, you are always welcome to subscribe, leave a gentle like, or share in the comments where you are listening from tonight. There is something comforting in imagining all of us, in different rooms and different time zones, pausing together to think about the same darkness between the stars. Now let us begin close to home, because the only way to understand the deepest emptiness is to start with the kinds of fullness we already know. Right now, wherever you are, the room around you probably feels empty in the ordinary sense. There may be furniture, walls, blankets, curtains, maybe a faint light somewhere, maybe rain outside, maybe the soft noise of a fan or distant traffic. But even if the room looks empty, it is full of air. Every breath you take is proof of that. Air is invisible enough that we often forget it is there, yet it presses against your skin, moves through your lungs, carries scent and sound, and fills every available space. A single cubic meter of air, roughly the amount that could fit inside a large box or a small closet, contains an unimaginable number of molecules. Not thousands, not millions, not billions, but on the order of 25 septillion molecules at room conditions. The number is so large that it stops being useful to speak it aloud. The point is simpler than the number itself. What feels empty to you is, in truth, overwhelmingly full. Now imagine going high above Earth, to the top of the atmosphere, where the air becomes thinner and thinner. Climbers on high mountains know that breath grows harder even long before you leave the atmosphere entirely. At commercial flight altitude, the air is already thin enough that airplanes need pressurized cabins. Higher still, the atmosphere becomes more and more rarefied, until eventually it shades into space. By the time you reach low Earth orbit, where many satellites move and where astronauts have traveled, you are in an environment that most people would comfortably call outer space. And outer space is indeed a vacuum by human standards. But even there, it is not perfectly empty. There are still particles. There are still traces of the upper atmosphere. There is still enough lingering matter that satellites slowly lose energy and require careful planning. Already, then, we begin to see a pattern. Empty is a relative word. Even space near Earth is not the deepest emptiness the universe has to offer. Now move farther out, across the solar system. Between Earth and the Sun, and beyond the planets, the density of particles drops dramatically. The solar wind, a stream of charged particles from the Sun, flows outward through the system. There is dust, there are magnetic fields, there are occasional traces of gas, there are cosmic rays moving through. It is extraordinarily thin compared to any environment on Earth, but again, it is not nothing. Then we go farther still, beyond the main crowding of the solar system, and out into interstellar space, the space between stars inside a galaxy. This, for many people, is where the imagination naturally stops. The space between stars already feels like the ultimate emptiness. The nearest stars are separated by light years. Most regions between them are dark and cold. And yet even interstellar space, inside a galaxy like the Milky Way, still contains more matter than the space between galaxies usually does. There are thin clouds of gas, drifting dust, magnetic fields, cosmic rays, and all the invisible background architecture of galactic life. Interstellar space is sparse. Intergalactic space is sparser still. This is the moment where the scale becomes hard to narrate to oneself without pausing. Inside the thin gas between stars in the Milky Way, the density can vary widely. Some clouds are dense enough to form stars. Other regions are more diffuse. But even the emptier parts of interstellar space may contain around 1 atom per cc, sometimes more, sometimes less, depending on the region. That may sound like almost nothing, and on a human scale it is. But a cubic centimeter is tiny, about the size of a sugar cube. Now let us compare that with the average density of ordinary matter in intergalactic space. In the great darkness between galaxies, the density can fall to about 1 atom per cubic meter, sometimes only a few, sometimes less than 1 on average in the deepest cosmic voids. A cubic meter. Not a sugar cube. Not a spoonful. A cubic meter is a box large enough to imagine standing beside. A volume of space roughly the size of a washing machine, or a closet, or a small piece of a room. And in that entire volume, there may be just 1 lonely atom. Sometimes not even that. It is difficult to overstate how empty that is. If the air in your room were thinned down to that degree, it would no longer resemble air in any meaningful sense. Sound would not travel through it the way it does here. Breathing would be impossible. There would be no cloud, no haze, no visible sign of matter at all. It would not feel like a very thin atmosphere. It would feel like the complete disappearance of atmosphere. And still, even that comparison fails to fully communicate the emotional scale of the emptiness, because we are used to thinking of atoms as small but present. We imagine 1 atom as a tiny thing, yes, but still something. What we forget is that 1 atom in a cubic meter means not only that matter is rare. It means distance between particles becomes absurdly large relative to their size. Matter is not merely diluted. It is almost abandoned. To feel this a little more clearly, imagine a large cathedral at night, silent and dark, with empty floor space stretching beneath the ceiling. Now imagine that all the air inside that cathedral, every drifting molecule, every invisible trace of gas, were removed until only a handful of isolated particles remained, each separated from the next by distances that, on the scale of particles, would feel enormous. Not crowded, not floating in visible suspension, but effectively alone. That begins to hint at the emotional texture of intergalactic emptiness. Or imagine a desert so vast that you could walk for years without seeing another person, another animal, another structure, another sign of life. Then imagine that even this is still much too crowded as an analogy, because deserts at least contain grains of sand, air, heat, wind, and horizon. Intergalactic space has less than that. Less texture. Less interruption. Less event. 1 atom per cubic meter is not emptiness the way a beach is empty in winter. It is emptiness approaching the limit of what nature allows. And yet the story becomes even more severe when we move from the average intergalactic medium into true cosmic voids, the largest underdense regions in the universe. These are the great hollow places between the filaments of the cosmic web. In such regions, the density can be several times lower than the already astonishingly low average. In the deepest parts of a void, you may find only a fraction of an atom per cubic meter on average. This sounds impossible at first, because how can you have a fraction of an atom? But the meaning is statistical. Across a very large region, the average amount of matter per cubic meter becomes less than one atom. Some cubic meters may have a particle, others may not. Spread across millions of light years, the average settles into a number so close to zero that human language can only circle it. This is where a simple phrase becomes unexpectedly profound. Almost nothing. Not dramatic nothing. Not philosophical nothing. Not abstract nothing. Physical almost nothing. The kind of nothing that still contains a few particles, a little radiation, and the faint pulse of the universe, but so little of each that emptiness remains the dominant reality. Another way to approach this is through the vacuums we can create on Earth. In advanced laboratories, scientists build vacuum chambers designed to remove as much matter as possible. These are engineering achievements of incredible precision. Pumps remove gas. Surfaces are treated carefully. Every effort is made to produce a near-empty environment for sensitive experiments. And these chambers are impressive. But compared with the deep spaces between galaxies, even our best laboratory vacuums are still crowded. That is one of the quietly humbling facts of cosmology. Nature creates levels of emptiness that our most refined machines can barely imitate. The emptiest places ever made by human technology are, in some cases, still denser than the deep natural vacuum of intergalactic space. What we build with extreme effort, the universe produces simply by being vast. This is a useful reminder that scale itself is a force. The universe does not need perfect efficiency to create astonishing conditions. It only needs enough space. Given enough space, even a few particles spread thinly become almost indistinguishable from total absence. And scale is doing almost all of the work here. If you compressed intergalactic matter into a smaller volume, it would not seem special. A little gas, a trace of plasma, barely anything. But the universe stretches this trace across distances so immense that the dominant experience becomes darkness and separation. This is why the space between galaxies feels more than empty. It feels indifferent. It feels like a realm in which matter itself has become reluctant. You can see hints of this in the way astronomers are forced to detect the intergalactic medium indirectly. They do not usually point a telescope at empty space and simply photograph this material the way one might photograph clouds at sunset. Instead, they often infer it through absorption lines in the light of distant objects, through X-ray signals in clusters, through the behavior of matter under gravity, through careful measurements of faint effects that reveal what cannot easily be seen outright. The matter is there, but it barely announces itself. It leaves fingerprints instead of portraits. That, too, suits the tone of the intergalactic dark. Everything about it is subtle. Everything about it resists immediate attention. You do not encounter it the way you encounter a mountain or a storm. You discover it slowly, by noticing what it does to light, to motion, to structure, to the shape of the larger cosmic web. And perhaps that is one reason the space between galaxies fascinates people in such a deep way. It is not empty in a simple theatrical sense. It is empty in a patient, measured, scientific sense. Empty enough to change how we think about matter. Empty enough to make the stars and galaxies feel almost accidental. Empty enough to suggest that the universe, on its largest scales, is built not from fullness with gaps, but from gaps with occasional islands of fullness. That reversal matters. It changes the emotional geometry of the cosmos. We often imagine that the important things are the bright objects, and that the dark between them is merely where nothing much happens. But once you understand density, once you understand how rare matter really is on large scales, the universe begins to feel inverted. The emptiness is no longer the background. It becomes the main feature. Galaxies become the interruptions. The rule is not presence. The rule is absence. And yet, somehow, that absence is not bleak in the way it first sounds. There is a calm beauty in it, a kind of stillness that does not need to apologize for being sparse. The deep universe is not trying to impress us with crowding or decoration. It is vast, quiet, and patient. It makes room for distance. It allows light to travel for millions and billions of years with almost nothing to disturb it. The same emptiness that feels haunting is also what makes the cosmos legible. Without all that space, light from ancient galaxies would not reach us so cleanly. The universe's emptiness is part of how it tells its story. Think again of Andromeda, 5 million light-years away. Its light crosses that gulf because there is so little in the way. A denser universe would be murkier, more obstructed, less transparent to its own history. The emptiness between galaxies is not only dramatic, it is useful. It is what allows the universe to be seen across time. That gives the void a second character. It is not only a region of scarcity, it is also a corridor, a transmission medium, a silent road over which ancient light can travel. And that road is astonishingly clear because so little occupies it. If you were somehow able to move through deep intergalactic space, and if you could survive the cold, the radiation, and the impossible practical problems of such a journey, the most striking thing would not be what you encountered. It would be what you did not. No nearby stars. No visible gas clouds. No drifting dust bright enough to glow around you. Just distance. Dark in every direction. Perhaps an occasional faint galaxy so remote it barely breaks the blackness. And around you, in each enormous cubic meter of space, perhaps one atom, or less. That is not simply emptiness. That is the near erasure of matter. And once that settles into the mind, another question begins to rise naturally. If the universe is so empty on average, why does it not look evenly empty everywhere? Why are there places where galaxies gather into clusters and filaments, while other regions are left almost hollow? Why does matter form a pattern at all? That question leads us to one of the most beautiful structures in all of cosmology. Because emptiness in the universe is not spread randomly. It has shape. It has architecture. It forms regions. It forms boundaries. It forms vast cavities outlined by rivers of galaxies. And those cavities, those giant underdense regions, are among the largest structures the cosmos has ever made. That is where we go next, into the cosmic voids themselves. Part 5, the largest empty places in the universe. There are places in the universe so large, and so empty, that the mind almost refuses to believe they are real. Not empty in the casual way a quiet road feels empty late at night. Not empty in the way a field might look empty in winter, or a room might seem empty after everyone has gone home. Those kinds of emptiness still belong to the world we know. They still contain air, dust, sound, weather, history, and the invisible traces of ordinary life. The emptiness we are about to enter is of a different kind entirely. It is cosmic emptiness. The kind that stretches not for miles, not for planets, not even for star systems, but for tens of millions, and sometimes hundreds of millions, of light years. It is a form of absence so vast that even galaxies, the great cities of stars, become little more than border markers around its edges. And these places have a name. They are called cosmic voids. If the earlier parts of this journey have helped you settle down a little, or quiet the mind before sleep, you are always welcome to subscribe, leave a like, or share in the comments where you are listening from tonight. It is a calming thought, somehow, that while we talk about the greatest empty places in the universe, there are people hearing these words from apartments, quiet bedrooms, distant towns, coastlines, and sleepless cities all across the Earth. Now let us move gently into the idea itself. When most people first imagine the universe, they imagine it as a place where galaxies are scattered around like glitter on black fabric. A little uneven perhaps, but more or less spread through space. Some parts denser, some parts thinner, but still fundamentally random, as though matter was thrown outward and simply landed where it landed. That picture is understandable. It is also deeply incomplete. Because on the largest scales, the universe is not random in that loose, scattered sense. It has structure. Enormous structure. Matter did not simply drift into place like dust settling on a floor. Over billions of years, gravity slowly drew matter into patterns. It gathered, stretched, connected, and concentrated. Galaxies formed in lines, groups, clusters, and long filaments that span astonishing distances. And once astronomers began mapping the universe in 3 dimensions, something extraordinary became clear. The galaxies were not spread evenly through space at all. They were outlining something. They were tracing the edges of gigantic hollow regions. It is hard to overstate how strange that realization was. For a long time, the night sky had given us only a flat impression of depth. We could see points of light and faint smudges, but once better surveys began to chart where galaxies actually sit in relation to one another, the cosmos started to look less like a random scatter and more like a web. Dense regions here, threads there, great branching lines of galaxies, clusters at intersections, and in between, huge regions where very little existed at all. Those hollow regions are the voids. In a way, the name is perfect, because it sounds simple and almost too plain. A void. Just a gap. A blank space. But in cosmology, a void is not a small absence. It is one of the most dramatic things the universe can make. A cosmic void is an enormous region of space where the density of matter is far below average. There may still be a few galaxies inside, especially faint dwarf galaxies, and there is still that incredibly thin intergalactic medium we talked about earlier. But compared with the rich, bright filaments and clusters around them, these regions are profoundly empty. And they are immense. A typical cosmic void may stretch across tens of millions of light years. Many are larger. Some of the biggest known voids reach well over 100 million light-years across. There are a few especially famous examples that seem almost unbelievable when you first hear about them, like the Boötes void, which is often described as being roughly a few 100 million light-years wide. Pause there for a moment. A few 100 million light-years. It is such a large measure that language starts to behave differently around it. The phrase does not enter the mind the way a mountain height or a city population does. It floats there, abstract and weightless, unless we slow down enough to let it change shape inside us. So let us slow down. If light left one side of such a void and crossed straight through to the other side, it would travel for tens or hundreds of millions of years before emerging. Entire chapters of biological history on Earth would unfold in less time than it would take that light to cross one of the great hollow places in the universe. Dinosaurs rose and vanished in a shorter span than light needs to cross some cosmic voids. Mammals evolved. Humans appeared. Civilizations emerged. Languages were born and forgotten. And still, in that same span, a beam of light would still be making its way across one of these dark cosmic chambers. This is why voids are often described as some of the largest structures in the universe. Which sounds a little contradictory at first, because how can emptiness be a structure? We usually think of structure as something built from matter, something present, something solid or visible. But the universe does not always follow our instinctive categories. A void is a structure because it has shape, scale, boundary, and relation to the matter around it. It is not just a random patch of missing material. It is a consequence of how the universe organized itself. Matter gathered elsewhere, and as it gathered, Other regions were left behind. Over time, those underdense regions became larger and emptier. So the void is part of the architecture. It is not a flaw in the cosmic design. It is one of the main features of the design. A useful way to feel this is to imagine soap bubbles packed together in a sink. The thin boundaries where the bubbles touch form a network of delicate walls and edges, while the hollow interiors make up most of the volume. In some ways, the large-scale universe is similar. The bright matter we tend to focus on, the galaxies and clusters, lie more along the boundaries, while the great hollow spaces take up most of the room. Or imagine a sponge. From the outside, a sponge looks like an object, a thing, but most of its volume is actually holes. The solid material forms a connected network, but the emptiness dominates the interior. In much the same way, the luminous universe can mislead us. We are drawn to the bright structures and think of them as the main body of reality, when in fact most of the volume is held by the emptiness between them. This is one of the deepest perspective shifts in cosmology. The universe is not mostly galaxies with some gaps. It is mostly gaps, with galaxies marking the edges. And once you begin to feel that, the role of cosmic voids changes. They are no longer odd side notes, or exotic curiosities tucked away in astronomy books. They become central. They become the dominant terrain, the true background geography of the cosmos. Of course, no one sees a void directly in the same way we see the moon or a bright star. A void is recognized through mapping, through the positions of galaxies, through the realization that a region is missing what ought to be there if matter were spread more evenly. It is a little like understanding the shape of a valley at night by seeing the towns lit up around its rim. You do not see the valley itself glowing. You understand it through the absence between the lights. And there is something quietly haunting about that. A void is known by what is not there. It reveals itself through silence. Astronomers map galaxies across huge volumes of space, and where the density drops dramatically, the picture begins to open. Filaments stretch around broad underdense regions. Clusters sit at knots in the web. The voids appear not as sharply cut holes, but as vast, softly bounded zones of scarcity. Their edges are not like the walls of a room. They are gradual. Density increases as you move toward the filaments, and decreases as you move inward toward the central emptier parts. So entering a void, if such a thing were possible in a human journey, would not feel like stepping across a line. It would feel more like leaving a continent and heading into a deep ocean. At first, islands would still be behind you. Then farther apart. Then fewer. Then the horizon would empty itself. And finally there would be only distance in every direction, with perhaps the faintest glow of other structures impossibly far away. And this is where the emotional tone of cosmic voids becomes so powerful. Because they are not merely large spaces. They are large silent spaces. The stars inside a galaxy at least offer orientation. Even interstellar darkness is framed by the knowledge that stars surround you in the broader disk of the Milky Way. But in a void, the scale of separation becomes so overwhelming that familiar points of reference begin to disappear. A galaxy cluster near the edge may remain as a faint concentration in one direction, another filament somewhere far off in another. But much of the interior would feel like the universe has stopped trying to populate itself. That does not mean voids are perfectly sterile. As we said before, they are not literal nothingness. Some do contain galaxies, but these are far fewer, and often unusual in the sense that they evolved in relative isolation, away from the crowded environmental pressures of dense galaxy clusters. These lonely galaxies drifting inside or near voids can offer astronomers useful clues about what galaxies do when they are left more to themselves, without constant gravitational encounters and the disruptive influences of denser cosmic neighborhoods. That, too, is an interesting kind of thought. Just as isolated islands on Earth can produce unusual ecosystems, isolated galaxies in or near voids may preserve different rhythms of development. They still obey gravity. They still form stars. They still change over time, but they do so in quieter surroundings, with fewer close neighbors, fewer cosmic disturbances, and a very different environmental story. So even the universe's emptiest places are not useless or inert. They are laboratories of solitude. And there is another subtle beauty in that. Voids remind us that emptiness itself can shape things. A crowded environment changes what grows there. A sparse environment changes it too. The absence of disturbance becomes its own kind of influence. But how do these enormous hollow regions come to exist in the first place? The answer begins in the early universe, when matter was distributed much more evenly than it is now, though not perfectly evenly. Tiny variations existed. Slight overdensities here, slight underdensities there. The differences were small, but gravity had time, and time is one of the universe's greatest tools. Over billions of years, regions that were slightly denser than average pulled in more matter. As they gained more matter, their gravity strengthened, which helped them gather even more. This is how the rich structures of the cosmic web gradually formed: filaments, clusters, superclusters, dense intersections of matter shaped by gravity working patiently over immense spans of time. And the regions that started slightly emptier than average followed the opposite path. As matter flowed toward the denser regions, the emptier regions grew emptier still. They were not actively pushing matter away in any ordinary sense. Rather, the denser regions were winning the contest for material, and the underdense regions were being left behind. They lost the slow gravitational race. Their scarcity deepened. Their boundaries expanded. Their identity as voids became more and more pronounced. This is one of the reasons voids are so scientifically elegant. They are not accidents pasted into the universe afterward. They are the natural counterpart to structure formation itself. You cannot have the web without the holes. You cannot have the gathering without the leaving behind. The existence of clusters implies the existence of emptier regions around them. Matter, once allowed to move under gravity, does not build a uniform cosmos. It creates contrast. And perhaps that is one of the quietest truths in all of this. The universe gained shape by becoming uneven. Light gathered in some places, and darkness deepened in others. Richness and emptiness emerged together. There is also a strange psychological effect that happens when people first encounter the idea of cosmic voids. Galaxies are easy to admire. They are luminous. They are visually beautiful. Spiral arms, star clouds, glowing cores, elegant shapes. Voids, by contrast, sound like the absence of beauty. They sound like where nothing is happening. But that is not quite right. Voids are beautiful in a different way. Not because they are full of spectacle, but because they reveal the true scale of the universe. They strip away the illusion of crowding. They show us how rare matter really is. They turn galaxies from the default setting of the cosmos into the exceptions they truly are. And in doing that, voids make the galaxies more beautiful, not less. A single bright filament of galaxies stretched across the mouth of a dark void is more astonishing than a universe filled evenly with stars would be. Contrast gives structure its meaning. Silence gives sound its depth. Dark gives light its edges. A void is not the absence of wonder. It is the frame that makes wonder visible. There is something restful in that idea, perhaps because it mirrors ordinary life more than we usually notice. Meaning often depends on spacing. Music depends on pauses. A story depends on silence between the words. Even thought depends on a little inner emptiness, a little room in the mind. Without space, there is no pattern. Without absence, there is no form. The universe seems to know this instinctively. It does not fill every region with matter just to prove that it can. It leaves vast rooms unoccupied, and by leaving them unoccupied, it lets the occupied regions become legible. That may also help explain why cosmic voids can feel oddly emotional when you think about them long enough. They make the universe seem lonelier, yes, but they also make it seem clearer. The cosmos is not trying to hide how sparse it is. It is showing us openly that existence, on the largest scales, is something that happens against overwhelming emptiness. And still, within that emptiness, structures form. That contrast is almost enough to feel like a kind of cosmic poetry. Imagine, for a moment, what it would be like to stand inside a perfect model of one of these voids. Around you, perhaps, distant boundary galaxies would glow like faint threads on a far horizon. There would be no nearby crowd of stars, no local galactic disk overhead, no familiar sense of being embedded in something rich with light. Just distance. A still, patient blackness. Not dramatic in the way a storm is dramatic. Not frightening in the quick, sharp way danger is frightening. But vast in a slow, total way. Vast enough that it would begin to feel less like a place and more like a condition. You would not think, out there, that the universe is full. You would think the opposite. You would feel, more clearly than ever, that fullness is precious because it is rare. And that is part of what makes cosmic voids so important. They are not just curiosities for astronomers. They are perspective machines. They change the emotional proportions of reality. They show us that our galaxy, and even our local galactic neighborhood, lives on the edge of an astonishing emptiness. They show us that what feels normal to us, stars in abundance, is cosmically unusual. They reveal that much of the universe's history has been shaped not just by where matter gathered, but by where it did not. And once you see that, the next question becomes almost irresistible. If voids are the holes, what exactly is the larger pattern they are holes within? What is the shape of the network that surrounds them? How do galaxies, clusters, and filaments connect across the universe to produce these vast hollow chambers in the first place? That is where we go next. Because cosmic voids are only fully understood when we step back far enough to see the whole design they belong to. And when we do, the universe begins to look less like scattered islands in darkness, and more like an immense, delicate web, shining faintly around immeasurable empty rooms. Part 6, The Cosmic Web and the Shape of Everything. If you could rise far enough above the universe, if such a thing were even possible, and if your eyes could somehow adjust to distances measured not in miles or planets or even galaxies, but in hundreds of millions of light years, the cosmos would begin to change its appearance in a very unexpected way. It would not look like a random spray of light. It would not look like marbles scattered across a dark floor. And it would not look like an endless fog of galaxies filling space in every direction. Instead, it would begin to look like a web. A faint, delicate, almost ghostly network stretched across the dark. Long glowing threads. Dense knots where those threads meet. Vast hollow chambers between them. A kind of architecture written not in stone or steel, but in gravity, time, and the patient motion of matter over billions of years. This is what astronomers call the cosmic web. And once you see the universe this way, even in the imagination, it becomes very difficult to return to the old picture of space as a simple emptiness with galaxies sprinkled through it. The web changes everything. It tells you that the universe is not merely large. It is organized. It has texture on the grandest scales. It has shape. And perhaps most importantly for our journey tonight, it reveals that the great voids we have been drifting through are not isolated oddities. They are part of a much larger design. If these slow cosmic meditations help you unwind, you are always welcome to like the channel, subscribe, or leave a quiet comment telling me where you are listening from tonight. It is always strangely comforting to imagine these thoughts moving out into the night, into homes and cities and quiet rooms all over the world, while above all of us the same sky keeps its ancient silence. Now let us step back, far back, until even clusters of galaxies start to look like details inside a greater pattern. To understand the cosmic web, it helps to begin with something simple. Gravity does not like sameness. If matter is spread almost evenly through space, but not perfectly evenly, then the slightly denser regions will begin to pull in more matter. Slowly at first. almost imperceptibly. But over immense stretches of time, that tiny difference becomes more and more important. The denser places grow denser still. The thinner places are drained. A little unevenness becomes structure. This happened in the early universe. Soon after the universe began, matter was distributed far more smoothly than it is now. Not smooth in an absolute sense, but smooth enough that there were no galaxies yet, no stars, no clusters, no grand visible architecture. There were only slight fluctuations, small differences in density imprinted in the young cosmos. Tiny ripples, tiny irregularities, little departures from perfect sameness. And those tiny departures were enough. Because the universe had time. Time enough for gravity to work in silence. Time enough for dark matter to gather. Time enough for ordinary matter to fall into those deeper regions. Time enough for the first stars to ignite, the first galaxies to form, and then for those galaxies to collect into larger systems. What emerged from this very slow unfolding was not a neat grid, and not a random spray, but something more organic. Matter gathered into long filaments, like strands of a great three-dimensional net. At the intersections of those filaments, clusters and superclusters of galaxies grew. And between those luminous highways of matter, vast underdense regions remained, the cosmic voids. So the web is made of both presence and absence. The threads are the places where matter gathered. The voids are the places left behind. And neither makes sense without the other. This is one of the most beautiful things about the cosmic web. It is not merely a pattern of galaxies. It is a pattern of contrast. Light and emptiness defining one another. Structure and silence existing together. If you removed the voids, the web would lose its shape. If you removed the filaments, the voids would no longer be visible as voids at all. The grand design depends on both. In that way, the universe begins to feel less like a heap of separate objects and more like a single connected system. Galaxies are not just floating independently in space like boats lost at sea. They belong to filaments, and filaments belong to larger patterns, and those patterns stretch across distances so enormous that the mind has to keep pausing just to breathe around them. Take our own galaxy, the Milky Way. We often think of it as home, and of course it is, but cosmically speaking it is just one large galaxy among hundreds of billions in the observable universe. The Milky Way belongs to the local group, our small family of nearby galaxies. The local group itself belongs to a larger gravitational region often referred to as the Virgo supercluster in older descriptions, though modern mapping shows that we are also part of an even larger flow structure called Laniakea, a supercluster-scale region containing roughly 100,000 galaxies. The name Laniakea means immeasurable heaven. It is a beautiful name, and an appropriate one, because once you begin speaking in terms of superclusters, you are no longer describing neighborhoods in any human sense. You are describing continental scales of the cosmos. Regions where galaxies flow under gravity toward massive attractors. Regions linked into filaments, not just small local associations. Regions so large that even the Milky Way, with all its stars and planets and histories and quiet human evenings, becomes almost impossibly tiny inside the broader map. And even Laniakea is not the whole web. It is just one region of it. One knot, one branch, one subtle gathering of matter in the larger cosmic design. The web itself stretches across the observable universe. It is the largest pattern we know. When astronomers map galaxies across vast volumes of space, what they see is extraordinary. Galaxies line up along filaments that can span hundreds of millions of light years. Clusters sit where filaments intersect, like great cities at the crossing of highways. Superclusters trace broader regions of concentration. And in between, the voids open out like silent basins in a dark landscape. The visual impression, when rendered in maps and simulations, is almost biological. It can resemble neurons, or roots, or frost spreading across glass, or the branching of rivers seen from high above. The resemblance is not exact, of course, but it is enough to stir something in the imagination. The universe seems to build with the same quiet love of networks that appears elsewhere in nature. Not because the same causes are at work in every case, but because growth under constraints often produces patterns that feel like cousins to one another. That can be deeply soothing to think about. The cosmos, for all its scale and indifference, is not chaotic in the shallow sense. It is patterned. It organizes itself. It has long-range shape. Somewhere in that thought there is a curious comfort. The universe is vast beyond understanding, and yet it is not shapeless. If you could travel along one of these filaments, the experience would be unlike crossing a void. Instead of moving through the deepest emptiness, you would be following one of the universe's long rivers of matter. Galaxies would not be crowded close together by human standards, but they would appear more frequently than in the hollow interior of a void. Groups would give way to clusters. Matter would seem to have a direction, a lane, a subtle geography. You would feel, perhaps, that you were not simply moving through the universe but following one of its hidden roads. That is one of the reasons the cosmic web is such a powerful idea. It transforms space from a blank stage into a landscape. Not a landscape of fields and mountains, but of density and scarcity, of filaments and hollows, of intersections and expanses, a geography of matter itself. And yet even here, we have to be careful not to imagine the web too literally. These filaments are not ropes glowing brightly in visible light. They are not solid structures one could stand on or touch. They are patterns of distribution, regions where galaxies, gas, and dark matter are more concentrated than the surrounding space. The web is real, but it is delicate. Much of it must be inferred through surveys, simulations, and the subtle ways matter bends light and shapes motion. In fact, much of the cosmic web is thought to be dominated not by the stars and galaxies we easily see, but by dark matter. This is one of the great hidden facts of the universe. The luminous matter that makes galaxies shine is only a small fraction of the total matter content of the cosmos. Most of the matter that gives the web its gravitational backbone appears to be dark matter, invisible to our eyes and telescopes except through its effects. It gathers first. It shapes the large-scale potential wells. Ordinary matter then follows, falling into those dark frameworks, cooling, condensing, and eventually igniting into stars and galaxies. So the visible web, in a sense, is the illuminated version of a deeper invisible structure. The galaxies are like lights strung along a scaffold we cannot directly see. And once again, emptiness becomes more complicated than it first appeared. The dark between visible objects is not always empty of influence. The web is full of hidden architecture. Gravity reaches farther than light. Dark matter shapes what ordinary sight would miss. The universe is constantly reminding us that appearance is only the beginning of truth. This can make the cosmos feel strangely intimate and distant at the same time. Distant because its scale is overwhelming. Intimate because its logic is understandable, if we move slowly enough. A little more matter here, a little less there. A slight imbalance in the beginning. Gravity acting patiently. Time doing the rest. From such simple ingredients, a structure emerges so vast that light itself needs millions of years just to cross its smaller pieces. And perhaps that is why the cosmic web carries such emotional force. It takes the universe out of the realm of abstract size and places it into the realm of pattern. It gives us something to picture. Not merely a big emptiness, but a connected emptiness. Not merely galaxies far apart, but galaxies belonging to lines, nodes, and regions. It turns bewildering scale into a kind of map. Of course, even a map this large cannot fully comfort the human mind. There is still something haunting about it. Because once you recognize the web, you also recognize how little of space is occupied by the bright structures. The filaments are thin compared to the voids they surround. The knots are rare compared to the darkness between them. The web gives the universe shape, yes, but it also confirms the dominance of emptiness. The luminous network is delicate. The hollows are enormous. This may be why some people feel an almost spiritual quiet when they learn about the web for the first time. It is not just scientifically interesting. It rearranges one's sense of reality. It says that the universe is not full in the way we instinctively imagine. It is mostly room, mostly openness, mostly distance. And yet within that openness, a subtle order stretches from one end of the visible cosmos to the other. There is a kind of tenderness in that, not because the universe is kind in any human sense, but because it allows room. Room for light to travel. Room for galaxies to grow. Room for history to unfold slowly. Room for observers like us to wake for a little while inside one small galaxy, on one small planet, and realize that the darkness around us is not random, but shaped, and shaped magnificently. Another fascinating thing about the cosmic web is that it was predicted before it was fully observed in detail. As cosmologists built models of structure formation and ran simulations of how matter should evolve under gravity, a web-like pattern naturally emerged. Later, as galaxy surveys improved, the observed universe began to confirm this picture more and more clearly. This is one of those rare moments in science that feels almost poetic. The equations suggest a hidden architecture, and then the sky slowly agrees. That agreement matters. It tells us we are not just inventing a beautiful metaphor. The web is not a literary image pasted onto the cosmos because it sounds elegant. It is a genuine large-scale feature of reality. Still, it remains difficult to feel its scale without metaphor, so let us try one more. Imagine a vast dark plain, unimaginably larger than any earthly terrain, across which delicate glowing rivers spread and branch. At some crossings, there are radiant cities of stars, galaxy clusters, dense and massive. Between the rivers lie gigantic empty basins where almost nothing dwells. Now make the whole thing three-dimensional, not flat. Let the rivers become strands in space, crossing above and below one another, connecting in depth. Let the basins become chambers rather than valleys. Let every scale increase until light itself needs millions of years to cross from one district to the next. That begins to approximate the web, not as a perfect image, but as a feeling. A universe that is less like fog and more like lace. Less like a crowd and more like a network. Less like uniform fullness and more like structure suspended around tremendous emptiness. This matters for another reason too. Once we understand the web, the phrase, between galaxies, becomes richer. A galaxy may be between other galaxies inside a group. A group may sit inside a filament. A filament may border a void. A supercluster may form part of a broader flow. So the meaning of between changes with scale. It is not just the gap from one spiral galaxy to another. It is the relation between nodes and threads, clusters and hollows, local neighborhoods and cosmic architecture. The web teaches us that every distance belongs to a larger pattern, and it also prepares us for the next step in our journey. Because once you see the universe as a web, an irresistible question follows. What would it actually feel like to move through it? Not just to look at the map from far away, but to travel it. What would it be like to leave a galaxy, pass through the thinner outskirts of a filament, and then enter the great dark interior of a true cosmic void? How long would such a crossing take? How still would the darkness become? What would happen to your sense of direction, your sense of home, your sense of what counts as distance at all? These questions are where the web becomes personal, in the strange imaginative way astronomy can sometimes become personal. Because to understand the architecture is one thing, to drift through it, even in thought, is another. And that is where we go next. We have now stepped back far enough to see the design, the filaments, the knots, the clusters, the hollows. The universe has shown us its skeletal shape. Now we are ready to begin moving through it, slowly, and ask what it means to cross the dark spaces between the threads of light. Part 7. What would it be like to travel across the void? Now that we have stepped back far enough to see the cosmic web, with its bright filaments and its vast hollow chambers, it becomes possible to ask a more intimate question. Not intimate in the human sense, of course. Nothing about a cosmic void is human in scale, but intimate in the sense that we are no longer just observing the map from a safe distance. We are imagining movement, a path, a journey. We are asking what it would feel like, not only what it would mean. What would it actually be like to leave the familiar structure of a galaxy, drift beyond the busier threads of the cosmic web, and cross one of the great empty regions between them? At first, that can sound like a question from science fiction. And in practical terms, for creatures like us, it is. We do not have ships that can cross intergalactic space. We do not have bodies built for millions of years of travel. We do not have engines that can carry us between galaxies in any ordinary sense. But the imagination is still allowed to go there. Sometimes that is one of the gentlest gifts of astronomy. It lets us travel where we cannot go, and by imagining the journey slowly enough, it teaches us something real. Because even an imagined crossing can reveal the scale of the universe in a way that raw numbers cannot. If these calm night journeys help you unwind, you are always welcome to like the channel, subscribe, or leave a quiet comment about where you are listening from tonight. It always adds something warm and human to these enormous topics, knowing they are being heard in ordinary rooms beneath the same sky. So let us begin. Imagine that you are leaving the Milky Way. Not in a hurry, not in a blaze of cinema or noise. Just gradually, almost dreamlike, lifting away from our familiar spiral galaxy. Behind you, the Milky Way would still seem immense for a very long time. Its broad disk, dense with stars, would not vanish in an instant. It would remain a great band of structured light, a bright continent of suns spread across the dark. Even after traveling far beyond our local neighborhood, you would still feel its presence behind you, the way one can still sense the coastline long after a ship has left the harbor. At first, the journey would not feel empty in the deepest sense. You would still be inside the broader halo of the galaxy. There would still be globular clusters, faint outlying stars, diffuse gas, dark matter extending invisibly far beyond the bright disk, and the lingering gravitational identity of the Milky Way itself. Leaving a galaxy is not like stepping out of a room. It is more like leaving a city whose suburbs thin so gradually that you do not notice at first when you have truly left it behind. That is the first quiet lesson of intergalactic travel. Boundaries in the universe are often soft. Things fade before they end. Then, slowly, the Milky Way would shrink. This is difficult to picture because we are used to seeing it from within. We know the Milky Way as a river of stars across the night sky. But from outside, from far enough away, it would become what Andromeda is to us now, a great spiral island of light in a sea of darkness. You would begin to see your own home galaxy the way we see distant galaxies through telescopes, as an object, a whole, a shape rather than an environment. There would be something quietly moving about that. To watch your galaxy become small. To see home turn into one luminous pattern among many. To realize that all the history of Earth, every life, every language, every quiet evening and crowded city and forgotten century, all unfolded inside one thin spinning system that now fits comfortably into your view. And ahead of you would be Andromeda, or perhaps some farther destination, still impossibly remote. If your destination were Andromeda, the nearest major galaxy, the journey would span about 2.5 million light-years. That sentence is familiar by now, but its emotional meaning changes once you imagine the crossing. A light-year is not just a number in a textbook anymore. It becomes a measure of loneliness, of duration, of how long darkness can continue without changing very much at all. Suppose, for a moment, that you were traveling at the speed of Voyager 1, one of the fastest human-made spacecraft ever launched. Voyager moves at roughly 17 kilometers per second relative to the Sun. That is astonishing by human standards. On Earth, it would feel almost supernatural. But on intergalactic scales, it is barely motion at all. At that speed, reaching Andromeda would take tens of billions of years, longer than the universe has even existed in its current form. That fact matters, because it reminds us that the distances between galaxies are not merely difficult. They are, with present technology, effectively impossible. Even if you could travel 10 times faster than Voyager, or 100 times faster, the journey would still vastly exceed a human lifetime. Even at 1% of the speed of light, which is far beyond our current reach for anything like a crewed intergalactic mission, it would take around 250 million years to reach Andromeda, a quarter of a billion years. On Earth, entire ages of life come and go in spans like that. So when we speak of traveling between galaxies, we are speaking from the point of view of physics, not human practicality. We are imagining a crossing so long that ordinary life loses its place inside it. And maybe that is what makes the thought so strangely calming. It removes us from urgency. Out there, in the dark between galaxies, there is no rush that means anything. No missed train. No crowded morning. No impatient clock. Only distance, unfolding at a scale so vast that speed itself begins to feel like a local illusion. Let us go farther into the thought experiment. Imagine, just for the sake of feeling the journey, that you had a ship capable of moving at the speed of light. This is not something ordinary matter can do, as far as we understand. But let the imagination borrow the possibility, gently, without turning it into spectacle. At light speed, the crossing to Andromeda still takes 2.5 million years. That means that even traveling as fast as the universe allows, the darkness between two neighboring major galaxies remains a journey beyond any normal comprehension of time. You would leave the Milky Way and continue on for thousands of years, then tens of thousands, then hundreds of thousands, then a million years, and still you would not be there. This is one of the rare facts in astronomy that can almost make the universe feel more silent than large. Large is one thing, silent is another. Because a journey like that is not only long, it is uneventful. There are no frequent landmarks, no nearby worlds, no rich chain of bright stations between one galaxy and the next. The space between galaxies is not a road lined with destinations. It is mostly the opposite. It is a road defined by the near total absence of destinations. That changes the emotional tone of travel completely. Here on Earth, even a lonely road still has signs of habitation. A light in the distance. A passing vehicle. A town eventually appearing beyond the hills. Even a flight over an ocean is brief enough that the emptiness feels temporary. But the intergalactic void would make all of that feel crowded. For vast stretches of the crossing, nothing much would happen around you at all. This is important to understand. When people imagine space travel, they often imagine motion as something visibly dramatic. Stars streaking by, constant shifting scenery, an obvious feeling of crossing distance. But in reality, especially across intergalactic scales, motion through empty space might feel visually almost static. Distant galaxies would change position very slowly. The blackness around you would remain black. Nearby there would be almost nothing to rush past. Traveling through a galaxy at least offers stars as points of reference. Traveling through the void offers almost none. The journey would be defined not by what you pass, but by what you fail to pass. Imagine looking out through the viewport of such a ship. Behind you, the Milky Way would slowly become smaller, its spiral shape condensing into a distant glow. Ahead of you, Andromeda would remain maddeningly far away, a faint but steady destination. Around you would be darkness so complete that the word empty would begin to feel insufficient. Not because there is literally nothing there, but because there is so little there that the mind registers the absence far more strongly than the presence. You might pass through the occasional thin patch of intergalactic gas, You might encounter a few particles of the intergalactic medium, though far too little to see as a cloud or mist. Ancient radiation from the cosmic microwave background would still pass through you and through the ship, a faint whisper from the early universe. Cosmic rays might occasionally strike the vessel, reminders that violence elsewhere in the universe can still send particles across enormous gulfs of dark. But none of this would feel like scenery. None of it would break the dominant impression. The dominant impression would be stillness. This is what makes intergalactic travel so difficult to imagine honestly. It is not only remote, it is monotonous in the deepest possible sense. The void does not entertain you. It does not vary for your comfort. It does not offer frequent reassurance that progress is being made. It is millions of light years of almost uninterrupted separation. And yet, in another sense, that stillness is exactly what makes it beautiful. Because the emptiness between galaxies is not hostile in the dramatic, explosive way popular imagination often prefers. It is not constantly attacking. It is not full of obstacles. It is not busy with destruction at every turn. It is simply vast. Vast and cold and sparse. It is the kind of environment that overwhelms you not with action, but with patience. Patience beyond anything human beings naturally possess. If you traveled long enough through the void, your sense of importance might begin to change. On Earth, our lives feel dense with event. Every day full of choices, moods, noise, obligations, and small urgencies. Even our quiet moments are full by comparison. But out there, between galaxies, the scale of your own thoughts would begin to feel oddly local. The universe would not shrink to make room for your concerns. It would do the opposite. It would remain exactly as it is, and because of that, your concerns might begin to soften. Perhaps that is one reason people find these topics restful. The void puts pressure on the ego by removing its stage. There is no audience in intergalactic space. No immediate consequence. No nearby civilization waiting. No visible center. You are simply moving through a region where the cosmos has decided not to place very much at all. And slowly, that can become peaceful. Not the peace of comfort, exactly, but the peace of proportion. The peace that comes from realizing that reality is far larger and quieter than the mind's usual turbulence. There is another strange aspect to such a journey as well. Over long enough spans of time, the universe itself would not remain frozen while you traveled. Galaxies move. Structures evolve. Stars are born and die. The cosmic web changes slowly. If your crossing lasted millions of years, your destination would not be waiting for you in quite the same condition as when you left. Even Andromeda, slowly approaching the Milky Way under the pull of gravity, would continue its motion while you crossed the gulf. Travel is always also time travel in this sense, but intergalactic travel makes the truth impossible to ignore. You do not go to a fixed universe. You go to a universe that is becoming something else while you are on the way. And on even larger scales, the expansion of the universe adds another layer of strangeness. Some galaxies are so distant that the space between us and them is expanding fast enough to make future contact effectively impossible. Their light still reaches us if it was emitted long ago, but the deeper future may cut them off beyond the cosmic horizon. So there are destinations in the universe that are not merely difficult to reach. They are receding into a kind of permanent unreachability. Intergalactic travel, then, is not just a matter of building a faster ship. It is bound up with the deep behavior of spacetime itself. That may sound technical, but the emotional meaning is simple enough. The universe is not only large, it is becoming larger. And the farther you try to go, the more that fact begins to matter. Now let us return to the imagined crossing itself. Perhaps the most disorienting part would be the loss of familiar reference. Humans are creatures of local structure. We navigate by landmarks, by horizons, by changes in weather and light, by the sense that places differ from one another in obvious ways. But much of the intergalactic void offers almost none of that. You would have instruments, of course, in any realistic scenario. You would know where you were mathematically. But emotionally, experientially, you would be moving through a region where direction feels abstract. The darkness would not look significantly different 1 million kilometers farther on, or 1 billion, or 1 trillion. That is difficult for the mind because it denies one of our deepest intuitions, that movement should produce visible change. In the void, change is too slow and too subtle to satisfy that intuition. And yet perhaps, if the crossing continued long enough, you would begin to notice another kind of beauty. Not dramatic beauty, but minimal beauty. The beauty of a destination that brightens by imperceptible degrees over long ages. The beauty of watching one distant galaxy slowly become less faint. The beauty of knowing that all the silence around you is not emptiness in a careless sense, but the actual large-scale condition of the universe. A crossing like that would teach patience better than any philosophy. It would also teach that galaxies are rarer than they feel from inside one. From Earth, the night sky can give a false impression. Stars seem abundant. The Milky Way seems richly crowded. Even telescope images filled with galaxies can make the universe look packed with light. But traveling the void would strip away that illusion completely. It would make you live, moment by moment, inside the true ratio of things. A little matter. A lot of darkness, a few islands, an enormous ocean. And then, after ages of crossing, the destination would slowly begin to grow. Andromeda, once a faint distant spiral, would become more structured. Its disk would spread wider. Its companion galaxies would perhaps become visible. Its halo would begin to surround you before its bright body truly filled the view. You would not arrive suddenly. Arrival, like departure, would be gradual. The emptiness would begin to thin. Structure would return. The great silence would start to acquire context again. And perhaps that would be the most emotional moment of all. Not leaving home. Not enduring the dark. But seeing another galaxy become real. Seeing another island of hundreds of billions of stars emerge from the blackness and realizing that the universe, for all its emptiness, still contains another place. Very far away. But there. That is one of the reasons the space between galaxies matters so much. The void does not only separate the islands of light, it gives them meaning. It makes arrival meaningful because crossing was so long. It makes galaxies precious because they are rare. It makes light beautiful because darkness dominates the volume of the cosmos. Without the void, galaxies would just be crowded objects among other crowded objects. With the void, they become improbable lanterns in a universe mostly defined by distance. And that brings us naturally to the next question. If crossing the void is so empty, so still, so sparse, does anything actually move through it besides light and the occasional imagined traveler? Do particles cross it? Do stars ever wander there? Can black holes drift through it? Is the void truly quiet, or does it still carry traces of motion from one structure of the universe to another? Because even now, after everything we have said about emptiness, there remains one more layer of strangeness. The void is not busy, but it is not completely inactive either. And that is where we go next. Part 8. Does anything ever cross the void? After imagining the long, almost dreamlike crossing between galaxies, a natural question begins to rise out of the darkness. If the void is so empty, so patient, so nearly silent, does anything actually move through it at all? Or is it truly a kind of frozen absence, a place so spare that once you enter it, nothing ever really happens there? This is one of those questions that seems simple at first, and then slowly becomes more beautiful the longer you stay with it. Because the answer is not no, but it is also not yes in the busy, crowded way our everyday minds might expect. The space between galaxies is not full of traffic. There are no great visible migrations passing constantly from one galactic shore to another. No streams of ships. No glowing caravans of stars crossing from cluster to cluster in any scene the eye could comfortably follow. The void is still, above all else, a place of extraordinary scarcity. And yet, even there, things do move. Light moves. Particles move. Radiation moves. Sometimes stars are cast into the dark. Sometimes black holes may drift where almost nothing else does. And beneath all of this, invisible and silent, dark matter continues to shape the larger architecture of the universe. So the void is not dead. It is active in a quieter way. Not with bustle, but with traces. Not with crowds, but with crossings so rare and stretched across such huge distances that they feel almost ceremonial. If these calm explorations help you wind down at night, you are always welcome to like the channel, subscribe, or leave a quiet comment saying where you are listening from. It is always a strangely grounding thought, imagining all of us here on one small planet, talking softly about the most empty places in the universe. Now let us go back into the dark and ask what, exactly, can move through it. The first and most important traveler is light. In some sense, light is the great crosser of the void. It is what makes astronomy possible at all. The reason we know galaxies exist beyond our own is that light has spent millions, and sometimes billions, of years traveling through the immense dark between them. It has crossed the thin intergalactic medium, the great hollows of cosmic voids, the delicate framework of the cosmic web, and arrived here carrying stories from distant places. Every time you see a galaxy in a telescope image, what you are really seeing is a successful crossing. The light made it. It survived the distance. It passed through all that emptiness and arrived at a sensor, or a mirror, or a patient human eye. That alone is worth pausing over. Because we often think of the void as something that separates galaxies, but it is also the thing that allows them to communicate. Not intentionally, of course. Galaxies are not sending messages in the human sense, but their light crosses the emptiness and reaches us. Their history travels through the dark. Their shapes, their colors, their motions, their age, even some clues about their chemistry, all move across the void as light. So the darkness between galaxies is not only a divider, it is also a corridor. A silent corridor, but a functioning one. If the universe were much denser, this would be harder. Light would scatter more, collide more, lose clarity more quickly. The immense emptiness between galaxies, strange as it feels, is part of why the universe can be read at all. It gives light room to travel. And light is not alone. The void is also crossed by particles. Some of the most fascinating of these are cosmic rays. Despite the gentle name, cosmic rays are not rays in the ordinary sense of visible beams of light. They are mostly fast-moving particles, often protons or atomic nuclei, traveling at enormous speeds. Some are born in the violent aftermath of exploding stars. Some may come from supermassive black holes feeding at the centers of active galaxies. Some may be accelerated in environments so extreme that even now we are still trying to understand them fully. These particles can carry extraordinary energy. And when they are launched into intergalactic space, they may travel for immense distances. Imagine that for a moment. Somewhere in a galaxy very far away, a star dies violently. Or a black hole hurls energy outward in a jet. A particle is accelerated, flung into the dark, and begins its journey. It passes beyond the local structure of its home galaxy. It enters the thin spaces between galaxies. It continues onward through regions that, from a human point of view, are almost pure nothingness. For perhaps millions of years, perhaps longer, it travels. Not seen, not noticed. Just crossing. Eventually, one of these particles may strike a detector on Earth, or interact with our atmosphere, revealing that some quiet messenger from a distant violence has completed an impossible journey through the cosmic dark. This is one of the great paradoxes of the void. The emptiest places can still carry the aftermath of the most energetic events. Silence does not mean the universe has forgotten motion. It only means motion has become sparse enough that each trace feels miraculous. Then there is radiation more generally. Not just visible light, but all kinds of electromagnetic radiation move through the void. Radio waves, X-rays, gamma rays, faint ancient microwave radiation left over from the early universe, all of these pass through space. The void is not full of visible objects, but it is constantly being crossed by signals. Some were created recently, on cosmic timescales. Others are relics from times so early that galaxies themselves had not yet fully formed. In that sense, the void is not empty of history either. History passes through it continuously. The ancient afterglow of the early universe, the cosmic microwave background, still fills all of space. It is everywhere, even in the deepest emptiness. That means that in every true void, in every region where matter is almost absent, there is still a faint bath of old radiation, a soft relic from a much younger cosmos. So if you drifted through the void, you would not be drifting through perfect nothingness. You would be moving through a region crossed by light from stars, by radiation from active galaxies, by ancient microwaves left from the early universe, and by high-energy particles that began their journeys in violence far away. Stillness, yes, but not total stillness. And then we come to the more haunting travelers. Stars. Can a star cross the void? Not in the sense of a star casually leaving one galaxy and setting off on a comfortable journey toward another. That kind of image belongs more to poetry than to realistic astrophysics. Stars are usually bound to galaxies. They live and die inside gravitational systems. They orbit galactic centers. They belong to larger structures. But sometimes, under the right circumstances, a star can be thrown out. Galaxies interact. Black holes merge. Gravitational forces pull and twist. In these complex encounters, a star can receive such a violent gravitational kick that it is ejected at enormous speed. Some of these are called hypervelocity stars. They move so quickly that they can escape the galaxy that once held them. That means there may be stars wandering in intergalactic space. Lonely stars. Homeless stars. Small points of fusion-driven light moving through the dark between the great galactic systems. This is a deeply moving idea, perhaps because it feels almost mythic. A star without a galaxy. A sun cast out from the structure that formed it, traveling through regions where there are almost no nearby neighbors, carrying its own little circle of light into the vast silence. And it is not only theory in the abstract. Astronomers have found evidence of stars outside the obvious boundaries of galaxies, especially in clusters where interactions can strip stars from their original homes. There is even a term for light produced by stars moving in the space between galaxies in a cluster, intracluster light. This faint glow comes from stars no longer cleanly bound to any one galaxy, but drifting through the shared gravitational environment of the cluster. That is not quite the same as a star crossing a giant cosmic void alone for hundreds of millions of light years. But it tells us something important. The universe does lose stars into the spaces between galaxies. It does let some of them wander. And once that is true, the imagination cannot help continuing the thought. Could such a star travel for extraordinary distances through the dark? Over long enough timescales, yes, motion can carry objects surprisingly far. But the distances involved remain immense, and the lifetimes of stars are finite. A star ejected from one region may travel through intergalactic space for eons, but whether it reaches another galactic system before changing or dying depends on the specifics of its speed, its mass, and the geometry of the larger cosmic structure. The important emotional truth is simpler. The void is empty enough that a single wandering star would not make it feel full. It would make it feel even lonelier. A lone flame in an enormous darkness does not erase the darkness. It reveals its scale. And what about black holes? This question, too, belongs partly to the realm of careful science and partly to the imagination. Black holes normally form from stars or grow in galaxies, especially the supermassive black holes that sit at galactic centers. So, like stars, they are usually associated with larger structures. But galaxies merge, collisions happen, and gravitational interactions can become extraordinarily violent. In some scenarios, black holes may be displaced, ejected, or left wandering. A black hole crossing intergalactic space would be almost perfectly invisible unless it interacted with nearby matter or revealed itself through gravity. That makes the idea especially eerie. A dark object moving through darkness, unnoticed except by the subtle ways it bends what little light passes near it or disturbs the tiny amount of matter in its path. There is something deeply quiet about that image. Not monstrous, not cinematic, just hidden. A black hole alone in the void, carrying gravity through the near absence of matter, crossing regions where almost nothing else happens. Whether many such wanderers exist, and how often, remains an active subject of astrophysical study and inference. But the possibility itself teaches something important about the character of the void. The void is not sealed. It is permeable. Things can enter it. Things can cross it. Things can be lost to it. And then there are galaxies themselves, though here we need to be careful with our wording. Galaxies do not generally zip across the universe like travelers in the way the imagination might first picture. But they do move relative to one another. Gravity draws them, clusters shape them, filaments guide the larger patterns of motion, and the expansion of the universe stretches the space between many of them over time. So in a larger sense, the whole cosmic web is in motion. Matter flows along filaments. Galaxies fall toward denser regions. Clusters pull on surrounding structures. Voids expand as matter drains away from them. Nothing is really frozen. Even the emptiest places are part of a dynamic universe. This matters because the void can sound static when described too simply. We picture a black stilled chamber and assume the story ends there. But cosmology is gentler and more complex than that. The void is quiet, yet it participates in the larger evolution of the universe. It is not busy on human timescales, but over billions of years it changes. Matter leaves it. Boundaries shift. Galaxies at the edges move. The structure deepens. Emptiness itself becomes part of the motion. There is also dark matter. We cannot speak honestly about what crosses the void without speaking about the invisible matter that makes up so much of the universe's mass. Dark matter does not interact with light in the ways ordinary matter does, so it cannot be seen directly in the usual sense. But its gravity shapes the cosmic web. It influences how galaxies cluster, how structures grow, how matter moves. Does dark matter cross the void? In one sense, dark matter is already part of the deeper architecture surrounding and underlying everything we are discussing. It is not a visible caravan of particles flowing past the way one imagines wind or water, but it participates in the gravitational patterns that define the web itself. Matter is pulled, structures emerge, underdense regions deepen, overdense regions gather more strongly. Dark matter is central to that story. So even where visible things are scarce, invisible influence remains. This may be one of the most mysterious aspects of all. The void can look almost empty to every ordinary human instinct, and yet it is still part of a universe whose behavior is being shaped by something we cannot see. The darkness is not only full of almost nothing, it is also shaped by hidden presence. And that makes the whole idea of crossing more subtle. When something moves through the void, it is not traveling through a neutral blank. It is moving through spacetime itself, through faint radiation, through a thin intergalactic medium, through the broader gravitational framework of dark matter and cosmic structure. The journey feels empty because the visible matter is so sparse, but reality remains layered. Even neutrinos deserve a quiet mention here. These tiny, elusive particles pass through matter so easily that vast numbers stream through your body every second without leaving any sensation at all. They are produced in stars, supernovae, and other energetic processes. The universe is full of them. Most pass unnoticed through everything, including the deep spaces between galaxies. Their existence is another reminder that emptiness is never simple. The void is not visibly populated, but it is constantly being crossed by some of the most ghost-like particles in nature. So by now the answer to our question has become clearer. Yes, things cross the void. Light crosses it. Radiation crosses it. Cosmic rays cross it. Neutrinos cross it. Sometimes stars are thrown into it. Perhaps black holes drift through it. Dark matter shapes its larger motions. Galaxies at its boundaries move and evolve around it. And yet, for all of this, the void still remains overwhelmingly empty. That is the balance that makes it so haunting. Movement exists there, but sparsely. Activity exists there, but faintly. Crossings happen, but rarely enough that emptiness keeps its crown. This is an important emotional point, because otherwise one might accidentally imagine the void as secretly crowded after all. It is not. Learning that things pass through it should not erase the earlier truth. The great darkness between galaxies is still defined by how little there is. The travelers we have named are meaningful precisely because they are exceptions. The corridor is wide because so few things use it. And maybe that is what makes the whole subject feel so meditative. The void is not empty in the philosophical sense of absolute nothingness. It is empty in the physical sense of almost nothing happening across enormous scales. That is different, and in some ways more beautiful. Because it means the universe is not divided into places where reality exists and places where it does not. Reality exists everywhere. But in some places it gathers densely enough to make stars and galaxies and planets and living beings. And in other places it thins until all that remains are traces, crossings, whispers, and patient invisible influence. The void belongs to the second kind of place. And as we sit with that, another question begins to appear. How did the universe become this way? Why are there such vast hollow regions at all? Why did matter gather into islands and threads, leaving so much room between them? Why does the cosmos seem to prefer contrast, rather than a more even and comfortable distribution? Because the more we look at the crossings, the more we start wondering about the emptiness itself. Not just what passes through it, but why it came to exist on such a scale in the first place. That is where we go next. Part 9. Why did the universe become so empty? By now, the emptiness between galaxies has started to feel less like a simple background and more like one of the main characters in the story of the cosmos. It is no longer just the dark space between brighter things. It is not just the pause between galaxies, or the quiet gap between islands of light. It is a condition, a structure, a presence of near absence. Something so large and so patient that it begins to shape how we think about existence itself. And once that realization settles in, another question begins to rise almost on its own. Why did the universe become this empty? Why is there so much room between the great structures of the cosmos? Why did matter gather into galaxies and filaments instead of remaining spread more evenly everywhere? Why is the universe, on its largest scales, a web of brightness suspended around immense dark hollows? It is one of the most beautiful questions in astronomy because the answer is not sudden. It unfolds slowly, like the universe itself. And to understand it, we have to go back, far back, not just millions of years, but billions. Back to a time before galaxies existed. Back to a time before stars had begun shining in the way we know them. Back to a younger universe, hotter, denser, smoother, and in some ways almost unrecognizable. If these slow journeys through science help you settle down at night, you are always welcome to subscribe, leave a like, or share in the comments where you are listening from tonight. There is always something comforting about pausing with a question this large and remembering that, for a little while, many of us are wondering about it together. So let us go back to the beginning of emptiness. When the universe was very young, it did not look anything like it does now. There were no spiral galaxies turning in the dark. No giant galaxy clusters. No cosmic voids opening across hundreds of millions of light years. None of the large, graceful structures we now see through our telescopes had fully formed yet. Instead, the early universe was much more even. Not perfectly even, but close. Matter and energy were spread out far more smoothly than they are today. If you could have looked across large distances back then, you would not have seen the dramatic contrast between dense galactic structures and enormous empty regions that defines the modern cosmos. The great emptiness had not yet matured. The web had not yet fully emerged. Reality was still in a younger, simpler state. This is one of the first things to understand. The universe did not begin as a finished landscape. It became one. The emptiness between galaxies is not something that was inserted afterward like decorative black paint around the stars. It grew out of the same long process that created the stars, the galaxies, and the cosmic web itself. The voids and the luminous structures are siblings. One cannot really be understood without the other. In the earliest times, after the hot beginning of the universe, matter was distributed with tiny irregularities. That phrase, tiny irregularities, is doing a great deal of work. These differences were extremely small, just slight variations in density. A little more matter here, a little less matter there. Nothing dramatic. Nothing that would have looked like a galaxy or a cluster or a vast hole in space. But those tiny differences mattered enormously. Because gravity notices even small imbalances. If one region has slightly more matter than another, then it has slightly more gravity. And if it has slightly more gravity, it pulls in slightly more matter. And if it pulls in slightly more matter, then its gravity grows stronger still. This is how structure begins in a universe that starts nearly smooth. Not all at once. Not with violence everywhere. But slowly, through amplification. A small advantage becoming a larger one. A faint unevenness becoming a pattern. This is where time becomes one of the great sculptors of reality. If you are patient enough, gravity can turn a whisper into architecture. Over hundreds of millions and then billions of years, matter began to gather into the denser regions. Dark matter, which does not shine but exerts gravity, played a major role here. It began to clump first, building invisible gravitational scaffolding. Ordinary matter, the stuff that eventually forms gas clouds, stars, planets, and people, fell into those deeper dark matter wells. Gradually, the denser regions grew denser, and the thinner regions grew thinner. That is the key idea. The universe became more structured by becoming more uneven. Some places gained matter. Other places lost relative importance. Matter flowed inward toward the growing structures, and in doing so, it left other regions behind. This is how emptiness deepened. Not because the voids actively pushed everything away in the beginning, but because gravity gave matter somewhere else to go. That is such an elegant process, and such a quiet one. The emptiness between galaxies is, in part, the result of matter choosing, under gravity, to gather elsewhere. A slight overabundance became a larger overabundance. A slight underabundance became a more pronounced underabundance. And so the cosmos slowly separated itself into two broad conditions, the places where matter gathered, and the places it increasingly did not. Over time, those places became the filaments and the voids, the islands of light and the oceans of dark, the web and the hollows. There is something almost natural history-like about it. You can imagine a broad landscape after rainfall, with water slowly collecting in the lower regions. At first the surface may look nearly uniform, but over time, tiny differences matter. Water begins to favor certain paths. Small channels deepen. Flow becomes organized. Some places become streams, others are left dry. Given enough time, a pattern appears that was not visible at the start. The universe did something a little like that, except the flow was matter under gravity, the timescales were billions of years, and the landscape was the deep architecture of spacetime itself. And then, within the denser regions, the next steps of cosmic history began. Gas clouds cooled. The first stars ignited. Galaxies assembled. Clusters began to form. These structures did not appear in the emptiest regions first. They appeared where matter had gathered most strongly. That means that the bright universe, the part we most easily admire, emerged in the places that won the slow gravitational contest. The dark regions, meanwhile, fell further behind. And so the modern universe came into being through contrast. The galaxies did not appear against a ready-made dark backdrop. The backdrop deepened as the galaxies formed. Light became more concentrated. Darkness became more expansive. They emerged together. This is one of the most calming truths in cosmology. The universe did not become beautiful by filling everything. It became beautiful by creating pattern. And pattern depends on difference. When we speak of the universe becoming empty, we should be careful with the phrase, because it does not mean matter vanished from the cosmos in any ordinary sense. It means matter became less evenly distributed. It collected into structures, leaving vast regions relatively underfilled. The total matter was still there, but it was no longer spread in a way that made every region feel alike. That distinction matters, especially for a beginner-friendly understanding of the universe. The emptiness between galaxies is not a hole punched through creation. It is what a structured universe looks like when matter gathers. And once galaxies had formed, they helped deepen that contrast further. Galaxies do not simply sit quietly forever. They evolve. Stars are born and die. Supernovae explode. Black holes feed and release energy. Galaxies collide, merge, and distort one another. Gas can be heated, stripped, or thrown outward. In clusters, large amounts of hot gas fill the spaces between galaxies. In some places, interactions cause matter to be redistributed. In others, galaxies consume or lose the raw material needed for future star formation. So the universe did not only become empty because of the first tiny irregularities and the long pull of gravity. It also became more differentiated as structures matured and evolved. Some places became rich with history and motion. Others remained sparse. The gap between full and empty grew easier to see. At the same time, the universe itself was expanding. This is another major piece of the story. From the earliest times onward, space itself has been stretching. Galaxies are not usually flying through a static void the way shrapnel flies through air. Rather, on the largest scales, the fabric of space between distant structures is expanding. This means that not only is matter gathering into filaments and clusters, but the overall stage on which this happens is also getting larger. So there are really two great processes unfolding together. Gravity gathers matter into structure. Cosmic expansion increases the scale of separation. Those two together create a universe in which dense regions can form while vast stretches of space continue to open between them. That combination is essential. If there were no gravity, matter would not have clumped into galaxies, stars, and clusters. The universe might have remained more diffuse and featureless. If there were no expansion, the story would also be different. But because both are happening, the cosmos develops into something rich in pattern, bright structures connected in a web, separated by growing regions of relative emptiness. At first, gravity dominated more strongly on many scales, especially in the denser regions. That is why galaxies and clusters could form at all. Matter had time to gather. Structures had time to grow. The universe was younger, smaller, and denser. The contrast between regions was increasing. But as time passed, expansion continued. And on the largest scales, another ingredient became more and more important: dark energy. We have touched on dark energy before, but now it enters the story of emptiness more directly. Dark energy appears to be a property of space itself that causes the expansion of the universe to accelerate. It does not dominate on small scales where gravity strongly binds matter together. That is why the Earth still orbits the Sun, why the Milky Way remains a galaxy, and why Andromeda is actually moving toward us rather than away from us. But on very large scales, where gravity is weaker and matter is spread thinly, dark energy matters a great deal. And where is matter most thinly spread? In the voids. This is one of the deep ironies of the cosmos. The emptiest places become the places where accelerated expansion is most free to shape the future. That means the universe is not only empty because matter gathered elsewhere in the past. It is also becoming emptier, in a large-scale sense, because expansion continues and dark energy helps drive the great structures apart. The filaments remain. The clusters remain. Galaxies inside gravitationally bound groups can remain together. But the wider spaces between these structures continue to stretch. The voids continue, in a broad sense, to win volume. This gives emptiness a different kind of role in cosmic history. It is not just what was left behind when matter clumped. It is also the arena in which the future of the universe is unfolding. As time goes on, the great empty regions become more important, not less. The universe, on the largest scales, becomes more dominated by separation. And this means that the emptiness between galaxies is not a temporary curiosity. It is part of the direction of the cosmos. There is something haunting about that, but also something strangely graceful. The universe begins hot, dense, and relatively uniform. Then gravity slowly gathers matter into structure. Galaxies ignite. The web emerges. Voids deepen. Expansion continues. And over still greater spans of time, the empty regions become ever more significant. In other words, the universe ages into spaciousness. That may be one of the calmest ways to say it. The cosmos grows older by becoming more open, more spread out, more silent between its great concentrations of light. If you pause with that long enough, it begins to feel less like a cold scientific detail and more like a very large kind of weather. Not weather in the earthly sense of rain and wind, but cosmological weather. A deep tendency in the universe. A slow drifting toward greater separation on the largest scales. This is not to say that all local structure fades immediately. Quite the opposite. Galaxies can remain rich and active for very long times. Mergers happen. New stars form. Groups and clusters can remain gravitationally bound. The Milky Way and Andromeda will eventually merge. Local drama continues. Gravity still matters enormously in the places where matter is concentrated, but the broader landscape grows emptier. The islands may remain, even change shape and merge. The ocean between them keeps widening. And perhaps that is why the modern universe looks the way it does. Not because emptiness was the original point, but because emptiness is what naturally becomes prominent when structure formation and cosmic expansion are allowed to work together for billions of years. The universe does not become interesting by filling every place equally. It becomes interesting by creating difference. A little more matter here, a little less there. Gravity amplifying the contrast. Expansion stretching the stage. Dark energy accelerating the great separations. And out of that, a universe appears that can contain both rich galactic life and immense dark quiet. When you think about it this way, even the phrase, space between galaxies, begins to change again. It no longer sounds like a leftover category, some accidental gap between more important things. It sounds like the natural result of the universe's long unfolding. It sounds earned. It sounds historical. The emptiness is not an afterthought. It is part of the story from the beginning. And it also means that the emptiness we observe now is not the final chapter. Because if dark energy continues to dominate the large-scale expansion of the universe, then the future will become even more spacious than the present, more isolated, more difficult for distant structures to see one another, more quiet, in a cosmic sense. This brings us gently to the final stretch of our journey. We have asked how far away the nearest galaxies are. We have asked what exists between them. We have felt how thin that nearly empty space really is. We have wandered through cosmic voids, traced the filaments of the cosmic web, imagined crossing the great dark, and asked what still travels through it. Now we are ready for the final question. What happens to all of this in the end? What becomes of the void as the universe grows older? Will the galaxies remain visible to one another forever? Or is the cosmos slowly moving toward an age in which emptiness becomes the dominant experience almost everywhere? That is where we go next. And perhaps it is the quietest question of all. Part 10, The Future of the Void, and the Quiet Fate of the Universe. There is something especially haunting about looking into the emptiness between galaxies once you realize it is not only a feature of the present, it is also a glimpse of the future. The dark spaces between galaxies are already vast beyond ordinary understanding. They already stretch across millions of light years, sometimes hundreds of millions. They already make galaxies feel like rare lanterns suspended in an almost endless sea of black. But as overwhelming as that emptiness feels now, the strange truth is that the universe is not done becoming empty. It is still moving in that direction. Slowly, quietly, patiently. So slowly that no human lifetime could ever feel it directly. And yet it is happening all the time, on the largest scales. The great web of matter is not frozen in place. The distances between its grander structures are still changing. The dark is still deepening. The void is still growing into its role. And if we follow that process far enough, if we let the imagination drift billions and then trillions of years into the future, the universe begins to take on a different character entirely. Less connected, less crowded, less visible to itself. The islands of light remain for a time, but the ocean between them keeps widening. The future of the cosmos, in the largest sense, belongs to the void. If these slow late-night journeys into science help you unwind, you are always welcome to like the channel, subscribe, or leave a quiet comment telling me where you are listening from tonight. There is something grounding about that, something warm and human, especially while talking about a future so vast that even galaxies begin to feel temporary. Let us stay with the present for one more moment before moving ahead. Right now, if we look out into the sky with powerful telescopes, we can still see a richly populated universe. We see galaxies by the thousands in deep field images. We see clusters, filaments, ancient light from distant epochs, and evidence of a cosmos full of structure. The night sky, once technology extends our sight, still contains other islands. We are not visually alone. That matters more than it first seems. Because this may not always be true. The expansion of the universe has been known for about a century. Galaxies on the largest scales are moving away from one another, not because they are simply flying through space like sparks from a fire, but because space itself is stretching. The farther away a galaxy is, the more of that expanding space lies between us and it, and the faster it appears to recede. For a long time, astronomers assumed that gravity might be slowing this expansion down. That was the natural expectation. Matter attracts matter. Galaxies have gravity. Clusters have gravity. So it seemed reasonable that the expansion might be gradually losing energy, like a ball rolling uphill against the pull of its own weight. But the universe surprised us. The expansion is not slowing down on the largest scales. It is accelerating. That is one of the most profound discoveries in modern cosmology, and it changes the long-term story of emptiness completely. Something, which we call dark energy, appears to be pushing the large-scale universe toward greater and greater separation. It does not rip apart galaxies or solar systems or atoms. Local structures that are strongly bound by gravity remain intact. But beyond those local scales, where matter is spread thinly and gravity is weaker, dark energy increasingly shapes the future. And where does it have the most room to act? In the vast spaces between structures. In the voids. This means the emptiest places in the universe are not passive blank backgrounds. They are the regions where the future is being written most clearly. The voids are where the expansion of space is most free to stretch, most free to widen the gulf between galaxy groups, clusters, and superclusters. So if we imagine the far future honestly, the first thing we have to imagine is this: the voids grow more dominant. Not because they become literally everything, but because the structures they separate become more isolated from one another. The web remains locally meaningful for a long time, but on broader scales it begins to loosen. The great filaments, the clusters, the superclusters, all of these stop feeling like parts of one visible shared landscape and begin to feel more like isolated provinces drifting farther apart in a deepening black. This does not happen tomorrow. It does not happen in a million years. It happens slowly enough to feel almost gentle. But gentle things, given enough time, can still transform everything. Let us begin with our own cosmic neighborhood. The Milky Way and Andromeda are not moving apart. They are moving toward one another. Gravity still dominates on the scale of the local group, which means the galaxies in our local family remain bound together despite the broader expansion of the universe. In around 4 to 5 billion years, the Milky Way and Andromeda are expected to begin merging in a long gravitational encounter that will reshape them both. Over time, they will become one larger galaxy, often nicknamed Milkomeda. That name sounds almost playful, but the event itself belongs to the deep calm of cosmic time. It will not be a single impact in the ordinary sense. Galaxies do not collide like solid stones. They pass through one another, distort, stretch, rearrange, and slowly settle into a new form. Their stars mostly avoid direct collision because galaxies are so full of empty space. Even a galactic merger is, in its own way, a dance choreographed by vast distance. So locally, the universe may actually feel more united before it feels more alone. Our nearby galaxies merge. Our local region becomes more consolidated. The night sky in that unimaginably far future would likely look very different from ours. Star patterns would shift. Structures would evolve. Entire chapters of stellar history would unfold. But the deeper change would be happening farther out. Beyond the local group, the rest of the universe would continue to recede. Clusters not gravitationally bound to us would drift farther away as space expands. Their light would become increasingly redshifted, stretched by the expansion of the universe into longer and longer wavelengths. Over enough time, that light would grow fainter and more difficult to detect. More distant structures would cross beyond what is sometimes called the cosmic event horizon, the point beyond which their future light can no longer reach us. This is one of the quietest and saddest ideas in all of cosmology. Not because something explodes, not because the universe ends in drama, but because more and more of it simply slips out of view. One by one, on enormous timescales, the distant galaxies disappear from the observable sky. Not all at once, not with any great cosmic announcement. They just fade, recede, redshift, cross the horizon. And then their future light never arrives again. Imagine a being in the unimaginably distant future, living inside the merged remains of our local group. Perhaps such beings, if they exist, would have advanced knowledge. Perhaps not. But unless they preserved the ancient evidence from our era, unless they inherited records or physical traces from the time when the sky was rich with galaxies, they might look outward and see almost nothing beyond their own galactic system. No grand cosmic web visible. No thousands of external galaxies scattered through telescopic surveys. No easy evidence that the universe was once crowded with visible structure. Just one great local galaxy, or the bound remains of a small local family, and beyond it an immense darkness. To them, the universe might look static and lonely. They might not even know that expansion was happening, because the clues would have drifted away. The large-scale evidence we rely on now could become inaccessible. The cosmic microwave background itself would be redshifted into wavelengths so long and faint that it might no longer be practically detectable. The very signals that allowed us to reconstruct cosmic history could fade beyond reach. This means we live in a surprisingly special era. That is not mystical language. It is simply cosmological perspective. We live at a time when the universe is old enough to have formed rich structure, yet young enough that distant galaxies are still visible. Young enough that the cosmic background radiation is still detectable. Young enough that the grand web has not yet been visually erased by the long-term consequences of expansion. We live during one of the few chapters of cosmic history when the universe can still be seen at scale. That is a remarkable thing, and perhaps a strangely comforting one, because it means the darkness between galaxies, frightening as it can sound at first, is also part of what makes our present moment meaningful. The void is large, yes, but not yet victorious in the total sense. Light still crosses it. Information still crosses it. The larger tapestry is still legible. The deep emptiness has not yet hidden the whole story from itself. But in the long future, that changes. The void becomes less like the space between structures and more like the defining reality around each isolated structure. The cosmic web, once visible as a grand connected pattern, breaks into islands that can no longer see one another. The universe does not necessarily lose all its matter. It loses its shared visibility. That distinction is important. Things still exist beyond the horizon. Other galaxies do not vanish from reality simply because their light no longer reaches us. But from any one local region, the observable universe becomes smaller in practical terms. The cosmos becomes partitioned by distance and expansion. Each bound system is left increasingly alone with its own stars, its own remnants, its own local history. And eventually, even the stars begin to change the tone of existence. Stellar formation does not go on forever. Galaxies use up or lose much of the gas needed to make new generations of stars. Over huge spans of time, the great bright era of star formation declines. Existing stars age. Massive stars die early. Smaller stars endure longer. Red dwarfs, the slow-burning, patient stars of the universe, continue shining for astonishing lengths of time. But even that is not forever. Trillions of years from now, the cosmos will be a quieter place than it is even in our most solemn imagination. Much of the bright stellar drama we now associate with galaxies will have slowed. Some stars will remain. Stellar remnants will remain. White dwarfs, neutron stars, black holes, cold worlds, dim objects drifting in old galactic systems. But the universe will have passed the vivid, youthful period in which galaxies glow richly with ongoing star birth. The darkness will not merely be between galaxies then. It will begin to settle inside them too. This is where the future of the void connects to the future of all things. The great emptiness between galaxies is only the beginning of a longer trend toward sparse existence. First, the large-scale structures become more isolated. Then the bright eras of stellar activity gradually fade. The universe becomes older, dimmer, quieter, and more spread out. Not suddenly. Not cruelly. Simply by continuing along the path its own laws have laid before it. This long future is sometimes discussed under the broad idea of heat death, though the phrase can sound harsher than the actual image. What it really describes is a universe moving toward thermodynamic exhaustion on the grandest scales. Energy remains, but useful gradients diminish. Structure persists in relic forms, but the vivid contrast of youth gives way to the gentler monotony of old age. Time continues. Space remains. But the cosmos grows quieter in what it can do. And through all of this, the void remains central. It is no longer just an impressive feature of the large-scale map. It becomes the dominant emotional tone of the late universe. Separation, stillness, patience, immense intervals between rare events. There is something almost oceanic in that vision, though even oceans are far too lively an analogy. Perhaps it is more like a universe aging into silence. Not total silence, because black holes may still merge, particles may still drift, rare interactions may still occur. But silence is the main condition. Silence is the background into which the last remaining structures slowly settle. And yet, there is another way to look at this. It is easy to hear all of this as a tragic story. A universe becoming lonelier, light fading, distances widening, structures growing isolated. But there is also a calm beauty in it, if we allow ourselves to see it differently. The universe is not failing when it becomes more spacious. It is simply continuing to unfold. Everything that exists has a rhythm. Stars have lifetimes. Galaxies have histories. Even the great web of matter has an era in which it is visible and an era in which it is not. The future emptiness of the universe is not a mistake. It is not a cosmic disaster in the human emotional sense. It is part of the same patient process that gave rise to the present beauty we now observe. The stars are beautiful because they are temporary. The galaxies are meaningful because they are rare. The web is magnificent because it can be seen now, and not forever. And perhaps the void itself is beautiful because it reveals the true scale of the story. It tells us that existence is not crowded by default. It tells us that light matters precisely because it travels so far through darkness. It tells us that connection, whether between galaxies or between moments of understanding, is precious because so much emptiness surrounds it. That may be the gentlest conclusion the universe offers. Not that everything lasts, but that what exists now is all the more extraordinary because it does not. If you step back and gather the whole journey together, the shape of it becomes clear. We began with a deceptively simple question about how big the void between galaxies really is. At first, it sounded like a question about measurement, a question about distance, a question that might be answered with numbers. But the deeper we went, the more it became something else. We discovered that even the nearest galaxies are separated by distances so vast that ordinary thought can barely carry them. We found that the space between galaxies is not perfectly empty, but so thin that the word empty still feels almost justified. We saw that the universe on its largest scales forms a web, and that the voids between its filaments are some of the largest structures in existence. We imagined crossing those spaces, wondered what still travels through them, and traced how the cosmos gradually became this uneven, spacious place. And now, at the end, we find that the void is not only a feature of cosmic geography. It is a direction of cosmic history. The universe is slowly becoming more void-like on the grandest scales. More separated, more isolated, more dependent on local islands of gravity surrounded by widening darkness. The future belongs less to connection across the whole and more to solitude within the parts. And yet, for now, we live before that final solitude. For now, light still crosses the dark. For now, the galaxies are still visible. For now, the sky still carries news from distant islands. For now, we can still look out and understand that we are part of something connected, however loosely, however briefly, across incomprehensible distance. That is no small thing. It means we are awake during one of the great readable chapters of the universe. And perhaps that is enough reason, on some quiet nights, to feel grateful for the emptiness rather than afraid of it. Because without the dark between galaxies, the light would not feel so miraculous. Without the silence, the message would not feel so clear. Without the void, we might never understand how precious these visible islands really are. So the future may belong to the dark. The universe may age into greater quiet. The great distances may widen until almost every galaxy disappears from every other sky. But tonight, at least for now, the light is still crossing. The story is still visible. And somewhere on one small world, under one small patch of that ancient sky, we are here to notice it.